The birth of radiation. From the Big Bang to the present. Before the first stars lit the heavens, before galaxies spun their arms through cosmic night, and long before the Earth ever cooled from its fiery beginnings, the universe was born in a single, searing moment. A burst of energy so immense, so absolute, that it forged both time and space. From this singularity came everything we know: matter, motion, gravity, and light. But among these primal creations, radiation stands as the first true messenger. It is the oldest remnant of the universe's awakening, a voice that has never fallen silent. In the first fractions of a second following the Big Bang, the universe existed as a hot, dense plasma, a chaotic sea of particles and radiation indistinguishable from one another. Temperatures were so high that particles such as quarks, electrons, and photons interacted constantly in a state of equilibrium. There were no atoms, no light in the classical sense, only raw, radiant energy tangled in the gravitational swell of the infant cosmos. As the universe expanded, it cooled. Within the first few minutes, nuclear reactions stitched protons and neutrons into the first light elements, hydrogen, helium, and traces of lithium. But light still could not roam free. Photons, the quanta of radiation, were trapped in a dense fog, scattering endlessly off-charged particles in a blinding glare of thermodynamic equilibrium. It would take hundreds of thousands of years for the universe to become transparent. This epoch, known as recombination, marks the true birth of cosmic radiation as a traveling wave. Around 380,000 years after the Big Bang, the universe had cooled to a point where electrons could combine with nuclei to form neutral atoms. With fewer free charges to scatter photons, radiation was finally liberated, streaming outward into the emptiness with almost no further interruption. This ancient light, cooled and stretched over billions of years, now bathes the cosmos as the cosmic microwave background, the faint afterglow of creation itself. It is the most ancient light we can observe, a fossilized imprint of the moment when silence and radiation first parted ways. But radiation did not cease its work there. As gravity pulled matter into clumps and filaments, forming the scaffolding of galaxies, radiation became the instrument of cosmic evolution. When the first stars ignited, massive, short-lived giants that burned hydrogen into helium and unleashed light, they ended the cosmic dark ages. These luminous pioneers flooded the universe with ultraviolet radiation, reionizing the hydrogen that had once turned opaque. They carved spheres of light into the intergalactic medium, illuminating the early universe and paving the way for future generations of stars and galaxies. From that moment forward, radiation became both witness and sculptor. It emerged not just from stars, but from every energetic event the universe could muster. Supernovae burst forth in brilliant flashes, flooding space with high-energy photons. Black holes, far from being completely silent, emitted powerful jets of radiation as matter spiraled toward their event horizons. Galaxies became factories of radiation, their cores sometimes lighting up with quasars, supermassive black holes feeding on surrounding matter and glowing with more light than entire galaxies combined. Across the spectrum, radiation diversified. Gamma rays, born from the most violent processes, such as neutron star mergers and gamma-ray bursts, traveled across space in narrow beams of energy. X-rays traced the hot plasma in galaxy clusters and the accretion disks of black holes. Ultraviolet light painted the canvas of night we see with our eyes. Infrared waves whispered of cooler stars, dusty nebulae, and hidden galaxies. Microwave and radio radiation mapped the large-scale structure of the universe and revealed the rotation of galaxies. On Earth, radiation forged the conditions for life. The sun's light, filtered by our atmosphere, provided not only warmth, but the energy necessary for photosynthesis, the very foundation of the biosphere. Radiation shaped climate, weather, and biology. Even the mutations that drive evolution are partly the result of radiation interacting with DNA. Life on Earth has evolved in a constant dialogue with light, balancing its nourishing warmth with the danger of its higher energy forms. But radiation is more than a local phenomenon. It is the carrier of information across space and time. Because nothing travels faster than light, all cosmic observation is necessarily a study of the past. When we look at the light of a distant galaxy, we see it not as it is, but as it was, millions or billions of years ago. Radiation is not merely energy, it is memory. It is the preserved echo of processes long finished, a continuous story written in electromagnetic waves. Even in the deep future, long after the last star has burned out, radiation will persist. As black dwarfs radiate the final whispers of thermal energy, as black holes evaporate through Hawking radiation, the cosmos will become ever quieter, ever colder, but never truly mute. Radiation will fade, stretching into longer and longer wavelengths, but its song will echo until there is no more energy to sing. Thus, from the furnace of the Big Bang to the silent drift toward entropy, radiation has remained a constant thread, a beacon, a chronicle, a force that defines the visible universe. And in the spaces between, in the shadows where no light has reached, silence waits. It is not empty, not meaningless, but a partner in the grand contrast of existence. Now, having traced the birth of cosmic radiation, we turn our attention to its incredible diversity. Light is not a single voice, but a full orchestra of wavelengths. In the next chapter, we will explore the vast spectrum of cosmic radiation: gamma rays, X-rays, ultraviolet, visible, infrared, microwaves and radio waves, and how each reveals a unique facet of the universe's unfolding story. Types of cosmic radiation: gamma, X-rays, infrared, and beyond. The universe, though vast and largely silent to our ears, speaks in a language of light. But this language is not confined to what the human eye can see. In fact, visible light is only a narrow window in a much broader electromagnetic spectrum, an ancient cosmic script that stretches from the most energetic gamma rays to the faintest whispers of long wavelength radio waves. Each type of radiation carries with it a distinct story, a unique perspective on the cosmos, and reveals structures, events, and forces that would otherwise remain invisible. Understanding this radiant diversity is to decipher the full symphony of the universe. At one end of the spectrum lies gamma radiation, the most energetic and penetrating form of electromagnetic energy. Born in the heart of the most extreme cosmic phenomena, gamma rays are emitted during the collapse of massive stars in supernova explosions, in the violent mergers of neutron stars, and within the turbulent environments near black holes. These high-energy photons can travel across billions of light-years, unaffected by magnetic fields or interstellar gas. Their discovery opened a new window into the catastrophic processes that shape galaxies and scatter elements into space. Gamma-ray bursts, for instance, are among the brightest explosions in the universe, outshining entire galaxies for brief moments, and are believed to signal the birth of black holes or magnetars. Following gamma rays are X-rays, a slightly less energetic form of radiation, but no less revealing. X-rays are forged in regions of intense heat and pressure, often where matter is being compressed or accelerated to extreme speeds. The hot gas in the cores of galaxy clusters glows in X-rays, allowing astronomers to map the hidden mass of the universe and trace the influence of dark matter. Accretion disks swirling around neutron stars and black holes emit powerful X-rays as matter spirals inward, heating up to millions of degrees. X-ray telescopes, stationed far above Earth's atmosphere, peer deep into these energetic arenas, exposing the skeletal framework of the high-energy cosmos. Descending the spectrum brings us to ultraviolet light, still invisible to the human eye, but vital to the universe's evolution. Ultraviolet radiation pours out from young massive stars, sculpting the gas clouds around them and driving the chemical reactions that create complex molecules. This radiation played a central role in the re-ionization of the universe, a transformative epoch when the first galaxies and quasars re-energized intergalactic hydrogen, clearing the fog left from the Big Bang and restoring transparency to the cosmos. Though partially absorbed by Earth's atmosphere, ultraviolet light is crucial in studying the life cycles of stars and the environments around distant exoplanets. At the center of the electromagnetic spectrum lies visible light, the sliver of radiation humans evolved to detect. This is the light of the sun, the stars, the galaxies whose ancient glow fills our night skies. Yet visible light is only a thin slice of a much richer spectrum. As we move to longer wavelengths, we enter the realm of infrared radiation, a domain of cooler temperatures and hidden structures. Infraradiation is emitted by dust, gas, and cold celestial bodies that are invisible in optical light. It is the glow of star-forming regions, cloaked in interstellar dust, of brown dwarfs too small to ignite into full stars, and of galaxies shrouded in ancient fog. Infrared observations penetrate the dusty veils that hide the birthplaces of stars and planetary systems, revealing the hidden nurseries where gravity assembles the building blocks of solar systems. It is in this spectrum that astronomers search for exoplanets and probe the thermal emissions of objects otherwise cloaked in darkness. The James Webb Space Telescope, designed to see the universe in infrared, peers further back in time than ever before, capturing light from the earliest galaxies born after the Big Bang. Further down the spectrum lie microwaves, best known for their role in cooking food on Earth, but far more significant on a cosmic scale. The universe itself emits a faint, nearly uniform microwave glow, the cosmic microwave background. This relic radiation is the afterglow of recombination, a whisper from the moment the universe became transparent, and it encodes information about the structure, composition, and ultimate fate of the cosmos. Variations in the microwave background, measured with exquisite precision, have provided evidence for dark matter, dark energy, and the geometry of space-time. At the lowest energy and longest wavelengths we find radio waves, the gentlest form of electromagnetic radiation. Despite their low energy, radio waves are among the most revealing tools in astronomy. They map cold, diffuse hydrogen gas between galaxies, detect pulsars ticking like cosmic clocks, and trace magnetic fields threading through interstellar space. Some of the most iconic cosmic structures, such as radio lobes extending from active galactic nuclei, are visible only in this spectrum. Radio astronomy also drives the search for extraterrestrial intelligence. listening for signals that might pierce the veil of silence in the stars. Each form of radiation interacts with matter in unique ways. High-energy gamma and X-rays reveal violent processes and compact objects. Ultraviolet highlights the youth and ferocity of stellar evolution. Visible light offers a direct view of starlight. Infrared unveils the cold and dusty regions of creation. Microwaves preserve the memory of the universe's birth, and radio waves trace the quiet rhythms of galactic dynamics. Together, they offer a complete portrait of the universe, a cosmos radiant in all directions, across all scales. The diversity of radiation is not merely a scientific curiosity, it is the foundation of observational astronomy. Because no single wavelength can tell the whole story, astronomers use the full spectrum to piece together the history, structure, and destiny of the universe. Each photon, regardless of its energy, carries a message from its source, whether a collapsing star, a spinning pulsar, a growing black hole, or a swirling galaxy. Light, in all its forms, is the most honest storyteller in the universe. And yet, for every voice that speaks in radiation, there is an answering silence. A silence that stretches between the stars and around the edges of galaxies, where the density of matter is so low that photons pass unchallenged and darkness persists. In the next chapter, we explore that silence, not as a void, but as a fundamental feature of the universe. What lies in the interstellar voids? And why does silence exist between the bursts of light? What secrets are held in the dark spaces where radiation fades and matter thins? It is in these silent zones that the contrast of the universe truly emerges. Silence between the stars. The nature of interstellar voids. Between the radiant voices of stars and the blazing signals of quasars, between the glowing filaments of galaxies and the swirling fury of black holes, lies something just as profound. Silence. Not the absence of existence, but the absence of radiant clamor. It is in these dark interstellar voids that the universe shows its other face, one not of noise, but of restraint. Not of chaos, but of stillness. These regions, often dismissed as mere gaps in the starry sky, are in truth among the most enigmatic and essential features of the cosmos. Interstellar space is not a perfect vacuum, yet compared to any environment familiar to human experience, it is extraordinarily empty. In the spaces between stars, regions that can span dozens or even hundreds of light years, particles are separated by distances so vast that a single cubic centimeter may contain only a handful of atoms. In contrast, the air we breathe contains trillions upon trillions of molecules in the same volume. This makes the interstellar medium, though not devoid of matter, one of the quietest regions in terms of particle interaction and radiation. But silence in this cosmic context is not only a function of emptiness, it is also a function of temperature, motion, and isolation. In the densest star-forming clouds, gas and dust clump together under the influence of gravity. These regions radiate in infrared and radio, betraying their structure through faint energy signatures. However, in the vast, diffuse expanses between these clouds, known as interstellar voids, the story changes. There, the temperature drops, interactions become rare, and radiation becomes faint or non-existent. Light may pass through, but very little is born within. This silence is not merely a passive feature, it is shaped by the life cycles of stars and the gravitational ballet of galaxies. When massive stars explode in supernovae, they sweep out nearby material, carving out vast bubbles of lower density. These supernova-blown cavities can grow to enormous sizes, bounded by shells of compressed gas but empty at their centers. These voids are essentially scars, cosmic hollows left behind by the violence of stellar death. Beyond the boundaries of individual stellar systems, the structure of the Milky Way itself contains vast regions of interstellar silence. While spiral arms are rich in gas, dust, and star formation, the spaces between them, the inter-arm regions, are marked by a relative quiet. In these zones, star formation slows, radiation dims, and gravitational activity is muted. It is within these quieter corridors that one begins to sense the vast, unspoken architecture of the galaxy. But silence, like light, carries information. The absence of radiation in certain wavelengths can tell scientists as much as its presence. By observing how light from distant stars dims or reddens as it passes through these quiet regions, astronomers can map the distribution of dust and infer the presence of otherwise invisible gas. The silence of the void becomes a negative image, a shadow etched onto the canvas of the cosmos. Moreover, interstellar voids play an essential role in the thermodynamic balance of galaxies. Without regions of low density to act as reservoirs and buffers, the cycling of gas between star formation and stellar death would break down. The silence between the stars is a kind of cosmic pause, allowing matter to cool, to settle, and to await its next transformation. In these places, molecules can form. Simple at first, like molecular hydrogen, but increasingly complex as conditions allow. It is in such cold, dark voids that the seeds of future stars and planets are sown. On a larger scale, the universe itself is structured like a web. Filaments of galaxies interlinked across vast expanses with immense voids between them. These cosmic voids, much larger than the gaps within galaxies, are the result of gravitational evolution. Matter has flowed into dense regions over billions of years, leaving behind enormous empty volumes that stretch across tens of millions of light years. These intergalactic voids are the most silent realms known. Places where galaxies are rare and radiation is thin, where the cosmic microwave background glows faintly and little else stirs. In their silence, these voids challenge our understanding of existence. They are not simply the absence of matter, but active participants in the gravitational structure of the universe. They influence how light bends, how galaxies move, and how space itself expands. Far from being voids in the dismissive sense, they are foundational to the geometry and dynamics of the cosmos. Silence, in this sense, is not nothingness. It is potential. It is the stage upon which all radiant drama unfolds. It gives meaning to contrast, allowing us to perceive not just what shines, but what does not. It is the echo of light's absence, the breath between stellar symphonies. In a universe dominated by radiation, silence is the frame, still and vast, against which the brilliance of the stars is set. And as we listen more closely to the universe, we find that even in these silent expanses, time leaves its mark. Charged particles occasionally drift through, energized by distant sources. Faint radio waves wander aimlessly across space. In some places, the silence is broken momentarily by a passing star or a rogue planet, cosmic drifters tracing paths through the dark. In others, silence remains unbroken for eons. Yet from these quiet depths, radiation inevitably returns. Somewhere, a new star forms from collapsing gas. Somewhere else, a black hole awakens with a burst of energy. Silence, it seems, is never permanent. It is always poised on the edge of change, and that change often begins in the most radiant places, the luminous nurseries of nebulae. In the next chapter, we will journey into these nebulae shaped not only by matter and gravity, but by the force of radiation pressure itself. Light becomes sculptor, silence yields to structure, and the interplay of energy and emptiness gives birth to celestial forms more intricate than any imagined by chance. Radiation pressure and the shape of nebulae. In the quiet reaches of space, where the echo of stellar birth lingers and clouds of gas drift through the void, there exists a force as subtle as it is mighty. Radiation pressure. This is not the pressure of wind or weight as we know it on Earth, but the cumulative push of light itself. Though massless, photons carry momentum, and when they strike particles of dust or gas, they exert a force. Over time, across the vast and delicate canvas of interstellar space, this force becomes sculptor, shaping the sprawling forms of nebulae into structures of breathtaking complexity. Nebulae, those ghostly clouds glowing in the night sky, are not static, featureless fogs. They are dynamic, ever-shifting regions composed of gas, plasma, and interstellar dust. Their forms can stretch for dozens or even hundreds of light years, painted in filaments, arcs, pillars, and voids. And while gravity, magnetism, and turbulence all play their roles in shaping these regions, radiation pressure emerges as one of the most powerful, yet often overlooked, shapers of cosmic art. When a massive star forms within a molecular cloud, it does not emerge quietly. Even before fusion begins at its core, the protostar radiates energy from the intense compression of matter under gravity. Once nuclear fusion ignites, the young star begins to pour out vast amounts of light and heat. This radiation sweeps outward in all directions, colliding with the gas and dust of the surrounding nebula. Every photon imparts momentum, pushing against the particles in its path. Over time, this sustained bombardment of light begins to clear away the surrounding material, carving out cavities and blowing vast bubbles through the cloud. One of the most iconic examples of this process is the Orion Nebula. In its heart lies a group of young, hot stars known as the Trapezium Cluster. These stars radiate intense ultraviolet light, which not only ionizes the surrounding hydrogen gas, causing it to glow, but also drives away the dust and cooler gas nearby. This interaction creates sharp-edged cavities, finger-like protrusions, and wispy curtains of material, all shaped by the invisible hand of radiation pressure. But this pressure does not act uniformly. The density and composition of the nebular material vary, meaning that some regions resist erosion more effectively than others. This uneven resistance gives rise to the towering pillars and ridges often seen in emission nebulae. The famed pillars of creation located within the Eagle Nebula stand as monuments to this process. Formed from denser pockets of gas that withstand the outward push of radiation, these pillars are slowly being eaten away, their edges sculpted into elaborate forms by the constant pressure of starlight. In addition to shaping structure, radiation pressure regulates star formation. As it clears away gas from young stars, it limits the amount of material available for other stars to form. In this way, light acts as both creator and limiter, forging stars even as it chokes off their siblings' birth. This feedback loop ensures that stellar nurseries do not collapse into a frenzy of uncontrolled formation, but instead proceed in waves, punctuated by intervals of stillness. Beyond individual stars and their immediate surroundings, radiation pressure also influences the evolution of entire nebulae. In starburst galaxies, galaxies undergoing intense periods of star formation, the cumulative radiation from thousands of newborn stars can drive outflows of gas from galactic cores. These galactic winds, propelled by combined radiation pressure, can span tens of thousands of light years, stripping galaxies of their gas and halting future star formation. Here, radiation not only sculpts but governs the future of cosmic structures on grand scales. Even the color and brightness of nebulae are linked to radiation. High-energy photons ionize specific elements, causing them to emit light at characteristic wavelengths. The red glow of hydrogen alpha, the green shimmer of doubly ionized oxygen, the deep blues of helium, these spectral fingerprints emerge because of how radiation excites atoms within the gas. Radiation pressure not only pushes matter, but also awakens it, turning inert clouds into glowing tapestries of color. Yet radiation is not a one-way force. The dust and molecules it encounters reflect, absorb, or scatter the light, often sending it off in new directions. This interaction creates reflection nebulae, where the starlight does not excite the gas but is instead scattered off dust particles, bathing the region in a cool bluish hue. In these places, the effect of radiation is gentler, more painter than chisel, giving rise to soft halos and veils of scattered light. As stars mature and die, they leave behind additional imprints in the form of planetary nebulae and supernova remnants. In planetary nebulae, the dying outer layers of a sun-like star are ejected and the remaining core emits ultraviolet radiation that excites the expanding shell of gas. The resulting glow and structure are dictated in part by radiation pressure, which shapes the expanding material into rings, bubbles, and ellipses. In more violent deaths, those of massive stars, the resulting supernova explosion blasts out matter at high velocity, but the shock waves that follow are also influenced by the star's radiation. The Crab Nebula, a remnant of such an explosion, pulses with high-energy light and displays an intricate web of filaments shaped by radiation and magnetism alike. Radiation pressure, then, is not just a physical force. It is a storyteller. It tells of birth and death, of resistance and collapse. It preserves the memory of stellar energy long after the star has dimmed. It explains the contours of distant nebulae, the brightness of their edges and the hollows in their hearts. It links the behavior of individual particles with the architecture of galactic arms. And this sculpting power of light connects to a deeper rhythm that echoes across the universe. The way stars flicker and pulse, the way their deaths imprint themselves in light, the way their spinning remnants continue to mark time in silence. From the shaped clouds of nebulae, we are drawn next to the rhythmic voices of collapsed stars, whose rotation and magnetism send out precise, repeated signals across the void. In the next chapter, we listen for these beacons, pulsars and magnetars, that emerge from the silent wreckage of stellar explosions, proving that even in death, stars can sing. Silent zones. Cold spots in the cosmic microwave background. Long after the first light of creation burst into being, when the universe was still a seething plasma of particles and photons, there came a moment of release. A moment when light could finally move freely, when electrons and protons cooled enough to bind into neutral atoms, and the universe became transparent. That ancient light still travels today. We call it the cosmic microwave background, or CMB. It is the faint afterglow of the Big Bang, and it fills every corner of space, a soft whisper of temperature spread across the sky. But within this gentle sea of uniform radiation, there are places where the whisper falters. Cold spots, silent zones, where something unusual lingers in the ancient fabric of space-time. The CMB is not perfectly smooth. It is marbled with subtle fluctuations in temperature, variations of only millionths of a degree, yet these tiny imprints hold the key to understanding the structure of the entire cosmos. These fluctuations were seeded by quantum perturbations in the earliest moments of cosmic inflation, microscopic irregularities magnified to intergalactic scales. Over billions of years, these ripples evolved into the vast web of galaxies, voids, and clusters that we observe today. Among these fluctuations are regions that are colder than their surroundings, colder than standard cosmological models can fully explain. These anomalies are not merely statistical noise. They are coherent, structured, and in some cases, deeply puzzling. The most famous among them is known simply as the cold spot, a region of sky in the southern hemisphere of the CMB map that exhibits a significant dip in temperature spanning hundreds of millions of light years. This cold spot was first detected in detail by the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite. Its presence raised questions that ripple through cosmology to this day. Could it be a statistical fluke, an unlikely dip that arises from the chaos of random variation, or is it the sign of something more exotic? Perhaps a vast supervoid, a region of the universe underdense in matter, which cooled the passing CMB photons through a process known as the integrated Sachs-Wolf effect. In the supervoid hypothesis, photons traveling through a large, underdense region lose energy as the universe expands. They enter the void with a certain amount of energy, but due to the region's lower gravitational pull, they exit with less. The net result is a slightly colder signal on the CMB map. Some surveys of galaxy distribution have, indeed, identified a potential void in the direction of the cold spot, yet the void's size and depth do not appear sufficient to fully account for the anomaly. The silence in that region, then, remains only partially explained. More speculative theories reach beyond standard cosmology. Some propose that the cold spot could be evidence of a collision with another universe in a multiverse scenario, where our observable cosmos is but one bubble among many in an infinite inflationary field. In this view, the cold spot is the cosmic bruise left behind from a moment when two universes brushed edges, disturbing the temperature distribution of our own. Though bold and still deeply theoretical, this possibility has not been entirely ruled out. Others suggest topological defects, relics from early phase transitions in the universe's history, might be responsible. These include phenomena such as cosmic textures or domain walls, theoretical wrinkles in spacetime that could leave an imprint on the CMB. If true, their discovery would fundamentally alter our understanding of the universe's infancy and the symmetry-breaking events that shaped it. Yet amid these grand interpretations lies a humbler and perhaps more powerful realization. The silence of these cold zones speaks to the remarkable precision of the universe's early conditions. The CMB is astonishingly uniform, almost eerily so, despite the unimaginable chaos of the Big Bang. The fact that cold spots stand out at all is a testament to the underlying order woven into the fabric of space-time. These anomalies are not distractions. They are clues. They are the fingerprints of a deeper reality, waiting to be deciphered. Moreover, the existence of silent regions in the CMB provides a kind of cosmic baseline. They are the places where radiation falls quiet, where entropy left a gentle shadow instead of a bright blaze. They remind us that silence is not absence, but texture, that even in the afterglow of creation, not all places shine equally. Some remember the stillness more than the spark. These zones may one day offer a test bed for the most daring ideas in theoretical physics about the shape of the universe, the fate of inflation, the presence of hidden dimensions, or the interplay between quantum fields and gravity. The silence they exhibit may not be random. Continue to map and measure the CMB with increasing precision. Future missions may reveal more about these zones, whether they are mere statistical quirks or cosmic relics of something deeper. In either case, their silence is a message whispered across 13 billion years of time. And this message, though faint, leads us next to more rhythmic voices in the night. For while the cold spot holds the silence of ancient creation, elsewhere in the cosmos, collapsed stars spin and pulse with metronomic regularity. Their light is not uniform, but chopped into bursts, beacons that flash across space with astounding precision. In the next chapter, we tune into those pulses, those cosmic lighthouses known as pulsars and magnetars, whose voices break the silence, not with randomness, but with rhythm. Pulsars and magnetars, rhythmic beacons in the dark. From the deep silence of cold spots in the cosmic microwave background, where the whisper of creation barely hums, we move into a vastly different kind of cosmic communication, one where silence is punctuated with stunning regularity, where the dead hearts of stars beat like ticking clocks across the darkness. Here, in this chapter of the universe, time is kept not by stars that shine steadily, but by objects that pulse. Flashing bursts of radio, X-ray, and gamma radiation with astonishing precision. These are the pulsars and magnetars, the rhythmic beacons of the cosmos, born not in peace, but in collapse. When a massive star exhausts its nuclear fuel, the fusion at its core can no longer resist gravity. In an instant, its vast structure implodes. What remains is not a fading ember, but a neutron star, an object so dense that a single teaspoon of its material would outweigh entire cities. These remnants, though only about a dozen miles in diameter, pack more mass than an entire sun. Their birth is cataclysmic, forged in the explosive final breath of a supernova, yet what they leave behind is among the most stable and precise natural mechanisms ever discovered. Pulsars are neutral stars that rotate with intense speed, often hundreds of times per second. They emit beams of electromagnetic radiation from their magnetic poles, and because these poles are misaligned with the star's axis of rotation, the beams sweep across space like the light from a lighthouse. To a distant observer, every time the beam crosses Earth's line of sight, a pulse is detected. Hence the name pulsar. These pulses arrive with such precise timing that the first discovered pulsar in the late 1960s was initially dubbed LGM-1 for Little Green Men, due to the possibility that it might be an artificial signal. But these were no alien transmissions. Instead, they were the echoes of extreme physics, proof that matter, magnetism, and motion could conspire to create cosmic metronomes. Pulsars are powered by their rotation. As they spin, they lose energy, slowly slowing down, yet many remain remarkably consistent over vast spans of time. Some pulsars, known as millisecond pulsars, spin so rapidly and consistently that they rival atomic clocks in precision. These can serve as natural detectors of gravitational waves, as any disturbance in the fabric of space-time would subtly affect the arrival times of their pulses. The magnetar is a more volatile cousin of the pulsar. Also a type of neutron star, magnetars possess magnetic fields 1,000 times stronger than typical neutron stars. Fields so intense they can distort atomic structures and potentially fracture the crust of the star itself. These cracks release bursts of high-energy radiation, creating dramatic X-ray and gamma-ray flares that can momentarily outshine entire galaxies. While pulsars are generally stable, magnetars are erratic, violent, and unpredictable. The power of a magnetar's field is almost beyond comprehension. It is trillions of times stronger than Earth's magnetic field, strong enough that if one were located within several hundred miles of Earth, its magnetic influence would erase credit cards, disrupt all electronics, and even alter the very chemistry of human biology. Fortunately, all known magnetars are far from our solar system, and their fury remains a phenomenon to be observed, not feared. Despite their explosive origins and their fearsome energies, pulsars and magnetars are profoundly valuable to science. Pulsars, for example, have been used to confirm the existence of gravitational waves. In binary systems, where two neutron stars orbit each other, the gradual decay of their orbits, as predicted by Einstein's general theory of relativity, has been tracked by pulsar timing, providing direct evidence of energy loss via gravitational radiation. Furthermore, pulsars have enabled astronomers to map the interstellar medium. As their radio pulses pass through space, they are affected by intervening electrons, causing dispersion and delay. By analyzing these effects, scientists can infer the density and composition of otherwise invisible regions of space. In a sense, pulsars are not only beacons, they are cosmic sonar, lighting up the dark and silent regions they pass through. And as navigational tools, pulsars may one day guide interstellar spacecraft. Their precise signals could serve as a kind of galactic GPS, allowing ships to locate themselves anywhere in the Milky Way with incredible accuracy. NASA has already tested this idea with the NISA mission aboard the International Space Station, which demonstrated autonomous positioning using X-ray pulsars, an extraordinary echo of how ancient sailors, once navigated by the stars, now translated to the vast distances between them. Yet the beauty of pulsars and magnetars goes beyond utility. They are evidence of nature's ability to create order from chaos, to forge rhythm from the wreckage of collapse. They remind us that even in death, stars can still communicate. Their messages are brief, intense, and consistent. Where the cold spots of the cosmic microwave background speak in stillness, these remnants speak in staccato bursts. Both are voices of the cosmos, just tuned to different registers. And these rhythmic voices mark more than just their presence. They mark time itself. They measure the age of the remnants around them, signal the presence of companion stars, and trace the expansion of the universe. They pulse on, regardless of who listens, etching their presence into the background of space like an ancient drumbeat echoing across an empty desert. As we continue our journey through the contrast of cosmic light and silence, the next stage brings us to echoes of a different kind, reflections of past brilliance that still flicker in space long after the source has dimmed. Light echoes, formed in the aftermath of supernovae. Light echoes are not sounds, And they are not signals in the conventional sense. They are delayed reflections of light itself, shadows of brilliance ricocheting through space long after the source of that light has gone silent. In them, the universe holds on to memory, preserving in faint flickers the grandeur of cataclysm. When a supernova erupts, a violent end to a massive star, it does so with explosive brightness. In mere moments, it can outshine its host galaxy, casting its brilliance across thousands of light years. But unlike the sound of an explosion, which fades in seconds and requires a medium to travel, light does not vanish so easily. It moves outward in all directions, and where it meets clouds of dust and gas, it is scattered and reflected, redirected toward observers far from the event itself. This redirected light reaches us later than the original burst, delayed by the longer path it has taken through space. What we see is not the supernova itself, but its echo, a visible memory suspended in space. These light echoes are not optical illusions. They are observable, measurable, and immensely valuable. They allow astronomers to study stellar explosions as if they are happening again, sometimes years or even centuries after the fact. In a way, light echoes turn dust into a cosmic recording medium. Each dust cloud becomes a screen, and the scattered photons project a brief film of the event. By observing light echoes from different angles and at different times, scientists can reconstruct the geometry and structure of the original explosion, gaining a three-dimensional view of a one-time event. One of the most celebrated examples of a light echo came from SN 1987A, a supernova in the Large Magellanic Cloud that exploded in the southern skies of Earth's hemisphere. Astronomers observed not only the brilliant explosion but also the rings of light expanding through space in the months and years that followed. These rings were not physical material being expelled. They were light echoes illuminating the surrounding dust in successive waves. Through them, we witness the reach of light bending around time, revealing layers of the supernova's surroundings and offering insights into the decades of stellar wind and material expelled before the final blast. But light echoes are not confined to recent history. They can also reveal events lost to direct observation. In our own Milky Way, astronomers have detected light echoes from supernovae that occurred centuries ago, long before the invention of the telescope. By tracing the delayed light reflected off interstellar dust, they have been able to study the properties of these long-dead stars, and even determine the type of supernovae that occurred. One such echo allowed scientists to analyze the supernova that formed the Cassiopeia A remnant, giving new understanding to an event last seen, if ever, in the 17th century. Beyond their utility in astrophysics, light echoes offer a rare and humbling philosophical gift. They demonstrate that the universe remembers, that even after destruction, some part of a star's final cry continues to move, reflect, and inform. The light of a supernova does not vanish, it travels, it lingers, and it waits to be found again. In this way, the cosmos becomes a kind of historian, preserving the past not in stone or bone, but in wave fronts of energy that paint the darkness long after the fires have gone out. Moreover, light echoes challenge our linear sense of time. When we observe a light echo, we are not just looking back in time, we are looking sideways through time. The supernova occurred in the distant past, and yet we are seeing new parts of it unfold today, not because the event is repeating, but because its light is being routed to us by cosmic geometry. Time in the universe is not just a river flowing in one direction. It is a sphere of light, expanding outward, touching surfaces, and returning to us with delayed glimpses of things long gone. The dust clouds that make light echoes possible are not uniform. Their shapes and densities affect the clarity and brightness of the echo. Some scatter the light cleanly, while others distort and diffuse it. Thus, every light echo is unique, a distorted but still meaningful remnant of an explosion's original form. This variation allows astronomers to study not only the supernova, but the intervening space itself. Light echoes become probes, revealing the size, shape, and structure of interstellar dust that would otherwise remain invisible. Even more remarkably, in a few rare cases, the spectrum of the light echo can be analyzed. This allows scientists to reconstruct the spectrum of the original supernova, determining its composition, velocity, and classification as if they were observing it live. Such observations bridge the gap between transient and timeless, letting us replay an event that, by its nature, seemed destined to vanish. In the cosmic dance of radiation and silence, light echoes stand as ephemeral sculptures of memory. They are not constant beacons like pulsars, nor are they as quiet and still as the cold spots of the CMB. Instead, they flicker briefly, moments of past brilliance mirrored in dust and then gone again. But in those flickers lies the fingerprint of some of the most transformative moments in the life of the cosmos. And these memories, preserved in dust and delay, transition us to another kind of silence, one that is not born of distance or destruction, but of the absence of matter itself. As we move from the memory of light to the silence of gravity, we encounter the event horizon of a black hole, where radiation is trapped and even light cannot escape. It is here, in the deepest gravity wells, that silence becomes absolute and light ceases to echo. In our next chapter, we explore the stark contrast between radiation and void within these cosmic prisons, the profound cosmic silence of black hole event horizons. Cosmic silence in black hole event horizons. As the dying light of a supernova reflects through the dust and whispers its memory in the form of a light echo, a more profound silence begins to emerge, one not of delay but of finality. It is the silence found at the edge of a black hole, the point beyond which even the memory of light is extinguished. Unlike the rhythmic beacons of pulsars or the flickering reverberations of ancient explosions, black holes do not pulse. They do not echo, and they do not reflect. They absorb, they silence, and they do so with such finality that no signal, no matter how powerful, can return once it crosses the invisible boundary known as the event horizon. The event horizon is not a physical surface. It is a threshold, a mathematical boundary in the geometry of space-time, a point of no return. When matter or light crosses this boundary, it is drawn irreversibly inward toward the singularity, the core of the black hole, where density becomes infinite and the known laws of physics falter. The escape velocity at the event horizon exceeds the speed of light, making it impossible for even photons to flee. To an outside observer, any object approaching the horizon appears to slow, redshift, and fade, ultimately freezing in place, dimming until it disappears from sight entirely. That disappearance is not just visual, it is communicative. It is the transition from noise to silence. This silence is not merely a consequence of darkness. It is a silence of information. In classical physics, black holes were considered perfect traps. Once information passed the event horizon, it was believed to be lost forever. That notion created a paradox. If black holes destroy information, then the universe itself would violate one of the core principles of quantum mechanics, which asserts that information is conserved. This paradox, famously raised by Stephen Hawking in the 1970s, remains one of the most troubling questions in modern physics. Hawking's work also introduced the notion that black holes are not entirely black. Through quantum effects near the event horizon, black holes emit a faint glow, now known as Hawking radiation. This radiation does not emerge from inside the black hole, but from quantum fluctuations at the horizon's edge. Particle-antiparticle pairs constantly pop into existence throughout space, and near the event horizon, one particle may fall into the black hole while the other escapes. To a distant observer, this looks like the black hole is radiating energy and slowly evaporating. Over unimaginable spans of time, black holes are thought to eventually dissipate, leaving behind nothing but radiation. But what happens to the information contained within them remains unclear. This unresolved tension between silence and memory defines the black hole's place in cosmic storytelling. If the universe is a narrative told through light, gravity, and time, then the black hole is its erasure, a place where stories end or perhaps pause in a way we do not yet understand. The silence of the event horizon is not absolute in the quantum sense, but it is absolute in the observational sense. It is the one place in the cosmos where no voice escapes, no beacon returns, and no echo can form. Yet, in its very silence, the black hole shakes the universe. It bends space around it, warps time near it, and influences the structure and fate of entire galaxies. The centers of most large galaxies, including our own Milky Way, contain supermassive black holes with masses ranging from millions to billions of suns. Their gravitational pull orchestrates the motion of stars and the dynamics of galactic arms, pulling material into violent accretion disks where it heats to incandescence before vanishing into the silent void. The paradox of black holes lies in their duality. They are both destroyers and creators. They extinguish light, yet shape light's path. They erase information, yet hold clues to a deeper physics, perhaps even a theory of quantum gravity that unites the seemingly incompatible realms of general relativity and quantum mechanics. Some physicists now speculate that black holes do not destroy information but encode it on the surface of the event horizon, a concept tied to the holographic principle. In this view, all the information swallowed by a black hole is preserved, not in its interior, but in a two-dimensional pattern at its boundary, as if the cosmos writes its secrets in layers of shadow. This opens an eerie philosophical mirror. The silence of the black hole may be illusory. What we perceive as absence might in fact be encoded presence. What we interpret as destruction might be compression, a waiting whisper written in gravitational script, illegible for now, but not necessarily lost. As the universe ages and cools, and as stars burn out and galaxies dim, black holes may become the final architects of cosmic evolution. In the distant future, long after the last star has flickered out, black holes may be the last active engines in a darkened cosmos, feeding, evaporating, and eventually fading themselves. Their long, silent reign will define the universe's twilight. Their final sigh of Hawking radiation will be among the last remnants of light. And yet, in the silence they impose, black holes make space for something remarkable. They shape regions of extreme contrast between brightness and darkness, between presence and void, between noise and stillness. They teach us that silence in the universe is never meaningless. It is structured, bounded, and in some strange way informative. It tells us where the known ends and the unknown begin. As we turn from these ultimate absorbers of light and sound, the journey leads us back to the realm of the listener. For if black holes represent the silence of cosmic consumption, then there is another kind of silence that stems from the absence of voice altogether, the eerie quiet of space as we search for messages from beyond, not from dead stars, but from other minds. The next chapter draws us toward the paradox of radio silence in our search for extraterrestrial intelligence, where we listen not for echoes of light, but for signs of language. Across the void, radio silence, searching for extraterrestrial signals from the absolute hush at the edge of black holes, a silence imposed by the boundaries of physics. We turn to a quieter, more haunting stillness, a silence born not from cosmic barriers, but from absence. This is not the kind of silence that bends light or devours stars. It is a silence that stretches across the vast reaches between civilizations, or perhaps across a universe where only one has ever existed. It is the silence of unanswered questions, of antennas raised to the sky with no reply. It is the radio silence that defines our search for extraterrestrial intelligence. Since the dawn of the space age, humanity has peered outward, not only to observe, but to listen. In the mid-20th century, with radio technology advanced and radio astronomy flourishing, a new scientific endeavor took root. The deliberate attempt to detect signs of alien intelligence through the radio waves that might carry their communication. This effort became known as SETI, the search for extraterrestrial intelligence. It was born from a profound and simple idea that intelligent beings, wherever they are, might use the universal language of physics, radio waves, to communicate across the stars. Radio waves are uniquely suited for such a task. They travel at light speed, require minimal energy to produce, and can cross immense interstellar distances with little absorption by gas or dust. Unlike visible light, which is scattered and easily obstructed, radio waves can pierce through the fog of the cosmos. They inhabit what scientists call the radio window, a relatively quiet and transparent portion of the electromagnetic spectrum that lies between natural sources of cosmic noise. For this reason, it is assumed that any technologically advanced civilization would recognize radio as an ideal medium for long-distance communication, just as we did. And so, we began listening. In the early 1960s, astronomer Frank Drake conducted Project Ozma, the first modern SETI experiment. Using a radio telescope in Green Bank, West Virginia, he tuned in to two nearby stars, Tau Ceti and Epsilon Eridani, hoping to catch a whisper of intelligent life. Though nothing was heard, the project marked a turning point. It showed that science could pursue the question of life beyond Earth not through speculation or fantasy, but through observation and method. Drake went on to formulate the now famous Drake equation, a probabilistic framework for estimating the number of detectable civilizations in our galaxy. While the equation itself contains variables so uncertain as to be almost symbolic, its value lies in shifting the question from "Are we alone?" to "What would it take for us not to be?" Since then, countless searches have been conducted, scanning the skies for narrowband radio signals, unnatural periodicities, or any emission that might suggest technological origin. Projects like Better, Serendip, and Breakthrough Listen have used some of the world's largest telescopes to comb through thousands of stars. In recent years, artificial intelligence and machine learning have been applied to comb vast datasets for patterns that human eyes might miss. Yet, despite decades of searching, we are met with a stunning absence of sound. No signals, no broadcasts, just the ever-present background hum of the universe, rich in natural emissions but devoid of artificial voice. This enduring quiet has come to be known as the Great Silence. And it raises the most profound question of all, not just, are we alone, but why does no one speak? There are many proposed answers. Perhaps intelligent civilizations are extremely rare, and we are a solitary miracle in an otherwise silent galaxy. Perhaps civilizations inevitably destroy themselves before developing interstellar communication, making silence a kind of cosmic tombstone. Or perhaps they are out there but do not use radio, having moved on to technologies beyond our understanding or deliberately choosing not to announce themselves. Others suggest the zoo hypothesis, that Earth is being deliberately avoided or quarantined, watched by advanced observers who choose not to interfere. There is also the problem of time. The window during which a civilization might use radio for communication could be brief, mere centuries out of millions of years. If two civilizations do not overlap in time, even if they exist in the same galaxy, they may never connect. The silence, then, would not mean absence, it would mean missed opportunity. Despite these challenges, the search continues, driven by a belief that silence is not final, only temporary. In a universe so vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars, it feels statistically improbable that intelligence has bloomed only once. Yet, the silence remains stubbornly intact. The paradox becomes sharper when we consider how noisy Earth has become. For over a century, we have been leaking signals into space. Television broadcasts, military radar, satellite communications. These signals have now traveled more than 100 light-years in all directions, forming an expanding shell of artificial radiation that announces our presence. Any civilization within that bubble, equipped with sensitive enough instruments, could detect us, and still no reply has come. Some propose that we should do more than listen, that we should speak. This approach, known as METI, messaging to extraterrestrial intelligence, argues that we should actively broadcast our existence with purpose and clarity. A few such messages have already been sent. The Arecibo message in 1974, a binary-coded interstellar postcard. The Voyager golden records, attached to spacecraft that now drift beyond the solar system. These are small steps, tossed bottles in a vast and cosmic sea. But speaking brings its own concerns. What if we alert a dangerous intelligence? What if silence is not ignorance, but a strategy for survival? The tension between hope and caution hangs heavy over our efforts to pierce the cosmic quiet. For some, the silence is reassuring, proof that danger has not yet found us. For others, it is tragic. Evidence that we remain unheard in a universe that may be rich with listeners. The radio silence, then, is not just a technical void, it is a philosophical mirror. It reflects our longing for connection, our fear of solitude, and our curiosity about what lies beyond. It challenges us to think about what it means to be intelligent, to communicate, and to exist in time. And so, with dishes pointed skyward and algorithms scouring the static, we wait, listening, always listening, for even a single artificial signal, One deliberate pulse amid the cosmic background would transform our understanding of existence. It would mean we are not the only voice to emerge from the dark. As we leave behind the long, empty frequencies of interstellar silence, the journey brings us back to more familiar, quieter realms, places close to home, where silence is not alien but natural. In our next exploration, we examine the airless surfaces of the Moon and other barren worlds, where silence is not metaphorical or philosophical, but physical and absolute. A silence born not of absence, but of atmospheric void. An environment where sound itself cannot exist. The quiet of the Moon and other airless worlds. In the long, uncertain search for voices beyond Earth, our instruments reach across vast light years. But after drifting through the deep hush of space, through the silence of black hole horizons and the unanswered frequencies of alien possibility, we arrive at a different kind of silence. Closer, more intimate, and far more absolute. This is not the cosmic silence of questions unanswered, but the physical silence of a place where sound simply cannot be. It is the quiet of the Moon, and of every other world where air has never stirred. The Moon, our nearest celestial neighbour, has been a symbol of mystery for millennia. From myth and poetry to the cold measurements of science, its pockmarked surface has fascinated humanity across every generation. Yet it was only when astronauts first set foot upon it that we truly encountered its quiet. When Neil Armstrong and Buzz Aldrin walked the lunar surface in July of 1969, they found not only a place of barren beauty, but a world utterly without sound. Their voices, their footsteps, the crackle of tools, all these existed only through the radios in their helmets. Outside their suits, the environment was perfectly silent. This silence arises from the Moon's most defining absence, its lack of atmosphere. Sound requires a medium, molecules of gas, liquid or solid, to vibrate and carry energy. Without air, there is no vibration and thus no sound. The Moon, with only the thinnest traces of exosphere particles, provides no such medium. It is a world where motion exists without noise, where violence erupts in silence, and where every impact, however violent, leaves only a mark, not a sound. Meteorites regularly strike the Moon, leaving behind craters and throwing up regolith in plumes of dust. These impacts can be massive, capable of reshaping entire regions of the surface. Yet each is a silent explosion. The energy released cannot travel through a vacuum, and so the cosmic violence plays out with mute finality. Seismic sensors placed by Apollo missions recorded the Moon's quakes, some lasting nearly an hour. But these were captured through direct contact, not airborne sound. Even the Moon's ringing like a bell, as some described its seismic response, was a vibration felt, not heard. The Moon is not alone in its silence. Across the solar system, many worlds echo this acoustic void. Mercury, scorched by the sun and blasted by radiation, is another airless orb where silence rules. Its rocky surface may crack and shift under extreme temperature changes, but these sounds never leave their source. Its proximity to the sun makes it an intense, hostile place. But even in its furnace-like conditions, there is no noise. Further out, we find the moons of Mars, Phobos and Deimos, small, irregular rocks tumbling through Martian skies. They are too tiny and too fragile to hold atmospheres. Silence surrounds them. On Europa, the icy moon of Jupiter, and on Enceladus, the Giza-spewing jewel of Saturn, vacuum dominates the surface, although both worlds show signs of subsurface oceans. Their outer shells remain hushed, and airless, even their geysers. Magnificent plumes of water vapor and organic molecules shooting into space erupt into nothingness, creating no splash, no roar, only visual spectacle. On Pluto, where sunlight is so faint that daytime resembles Earth's twilight, the silence is nearly complete. Its tenuous atmosphere, mostly nitrogen, collapses and condenses when it moves farther from the Sun, forming a world so still, so distant, that any sound would struggle to find a carrier. The dwarf planet lives in acoustic stillness, broken only by the dreams of telescopes that once glimpse its icy heart. What does this silence teach us? On Earth, we are surrounded by a world saturated with sound. Wind through trees, waves crashing on shorelines, birdsong at dawn, thunder splitting clouds. All these experiences are mediated by air. Sound is a constant companion, but when we journey into space, we must leave behind this sonic world. Even astronauts on the International Space Station, though surrounded by the low hum of machinery and life support systems, can never hear the external universe. Outside the metal hull is vacuum, an infinite silence that cannot be breached. In airless worlds, silence becomes a scientific asset. Without atmospheric interference, observations of cosmic radiation, solar particles, and the interplanetary medium become clearer. The Moon's far side, for instance, has long been proposed as a prime location for a radio observatory, shielded from Earth's electromagnetic noise. In that enduring silence, we might finally hear the quiet murmurs of the cosmos, unfiltered, if not by sound, then by signal. Yet there is also a profound psychological dimension to this quiet. For future explorers and settlers of other worlds, the absence of ambient noise could become disorienting, even haunting. On Earth, our brains are trained to interpret sound as a constant background of meaning and safety. Remove that layer, and the environment becomes alien in the most visceral sense. To hear nothing at all, even when moving, hammering, or falling. This is an experience so foreign that it may alter how we think, feel, and perceive. The quiet of airless worlds is thus not just a scientific condition, it is an existential one. These are places where life cannot breathe, where voices cannot carry, and where even memory must be encoded not in sound, but in texture, motion, and light. In that way they resemble black holes, not in mass or gravity, but in their refusal to carry voice. Yet unlike black holes, these worlds are open to us. We can walk upon them, touch their surfaces, and leave footprints that will last for millions of years, undisturbed by wind or rain or rustling branches. And so we return from the outer reaches of silence, cosmic, quantum, gravitational, to the intimate hush of rock beneath our feet. From the Moon to Mercury, from Europa to Enceladus, these worlds remind us that silence is not empty. It is shaped by physics, carved by history, and inhabited by potential. As we continue to explore these silent frontiers, we find that even in places where no sound can live, radiation does not rest. For while sound needs a medium, energy does not. Worlds without voices are still bathed in radiation, bombarded by solar wind, bathed in magnetic flux, cloaked in invisible belts of charged particles. In our next exploration, we travel deeper into this unseen realm, to the radiation belts surrounding planets, zones of violent energy dancing in silence, shaping life, threatening machines, and protecting worlds. Radiation belts around planets. Emerging from the total silence of airless worlds, we now confront a realm that is anything but quiet. Not in sound, but in energy. Though the vacuum of space forbids the vibration of molecules, it does nothing to still the storms of invisible radiation that wrap themselves around planets. These radiation belts are not static structures, but seething, shifting zones of energetic chaos. Unseen to the eye and inaudible to the ear, they are nevertheless crucial players in the evolution of planetary environments, the survival of spacecraft, and perhaps even the flourishing of life itself. The best-known radiation belts in our solar system are the Van Allen belts, named after American physicist James Van Allen, whose team discovered them in the late 1950s during the early years of the space race. Using data from the first American satellite, Explorer 1, scientists realized that Earth was surrounded by powerful bands of trapped, charged particles, mainly protons and electrons, held in place by our planet's magnetic field. These belts form toroidal or donut-shaped zones that extend thousands of miles above the surface, rotating and fluctuating with solar activity and geomagnetic storms. But what exactly are these belts, and why do they form? To answer that, we must consider the nature of planetary magnetic fields and the flow of solar wind. Our Sun constantly emits a stream of charged particles, plasma that races outward in all directions at supersonic speeds. When this stream of solar wind encounters a planet with a magnetic field, it is deflected and redirected, but some of these particles become trapped within the field, spiraling along magnetic lines and bouncing between the poles. Over time, these trapped particles accumulate, forming dense, energetic belts. Earth's magnetic field, generated by the dynamo effect of its liquid outer core, acts as both shield and snare. It protects the surface from deadly solar and cosmic radiation, yet in doing so, it creates regions where radiation becomes intensely concentrated. The inner Van Allen belt, located a few thousand miles above Earth, contains high-energy protons likely formed from the decay of cosmic ray interactions with the atmosphere. The outer belt, extending tens of thousands of miles farther, contains primarily electrons from solar wind. These belts can swell or shrink dramatically depending on solar storms, which inject new energy and reshape their boundaries. For decades, these radiation belts remained largely abstract to the public, but to engineers and astronauts, they became very real obstacles. Any spacecraft passing through these zones must be shielded from particle bombardment, which can fry electronics, degrade solar panels, and endanger human health. The Apollo missions, for instance, carefully plotted flight paths to minimize exposure during transit through the Van Allen belts, using speed and trajectory to limit astronauts' time in the danger zone. Even modern satellites in high orbits must account for the belt's influence, with many placed in geostationary orbit outside the most intense regions. Yet Earth is not alone in this phenomenon. Other magnetized planets, especially the gas giants, have radiation belts of far greater magnitude. Jupiter, the largest planet in the solar system, possesses a magnetic field 10 times stronger than Earth's, and its radiation belts are correspondingly immense. These belts are so intense that they pose a serious hazard to spacecraft. The Galileo probe, which orbited Jupiter in the 1990s and early 2000s, experienced repeated damage to its electronics. Even with hardened shielding, parts of the spacecraft degraded under constant bombardment. Jupiter's belts are fueled not only by solar wind, but also by material from its volcanic moon, Io. Io is the most geologically active body in the solar system. and its eruptions hurl sulfur and other elements into space, which become ionized and swept into Jupiter's magnetosphere. There they are accelerated to high energies, adding mass and fury to the radiation environment. In this way, moons and planets can interact in profound, dynamic ways, building electromagnetic ecosystems that are anything but silent. Saturn too possesses radiation belts, though less intense than Jupiter's. Uranus and Neptune have magnetic fields that are oddly tilted and offset, producing radiation belts of unusual shape and behavior. Each of these planetary systems presents its own electromagnetic puzzle, revealing the deep connection between magnetic fields, rotation, internal structure, and cosmic radiation. But radiation belts are not just hazards. They also protect. By absorbing and deflecting energetic particles, they create a buffer zone between the solar wind and the planet's atmosphere. Without this shield, Earth might have lost its atmosphere long ago, stripped away by unrelenting solar pressure, as seems to have occurred on Mars. Mars, with only a patchy and weak magnetic field, lacks global belts and suffers continual atmospheric loss. Its thin air and dry surface are a reminder of what happens when magnetic protection fails. In studying radiation belts, we are not merely cataloguing another cosmic phenomenon. We are probing the mechanisms that shape habitability itself. A planet's ability to shelter life may depend in part on the invisible barriers it raises against the vacuum of space. And as we look to exoplanets around distant stars, the detection of magnetic fields and their potential to form radiation belts may become a key criterion in the search for Earth-like worlds. These belts also teach us about high-energy physics in natural settings. Trapped particles in magnetospheres reach energies rivaling those in human-made accelerators. They offer laboratories for studying particle behavior, wave-particle interactions, and electromagnetic turbulence. The belts are not passive structures, but dynamic, living systems pulsing with energy, fluctuating with solar tides, and reshaping in real time. As we continue to send probes deeper into the solar system, understanding and navigating these belts will remain essential. They are at once guardians and gauntlets, defensive rings that protect planets while threatening intruders. In the quiet vacuum of space, they are among the most active and violent regions, invisible to the eye but deadly to unshielded life. From these radiation belts we trace an arc back toward the very heart of stellar death and rebirth. For while radiation belts surround living planets, light and silence continue their eternal struggle within stars reaching their end. In our next chapter, we delve into that final interplay, the dance of radiation and silence in the death of stars, where light flares and fades, and the universe writes its most poetic elegy in thermonuclear fire and gravitational collapse. The interplay of light and silence in the death of stars. From the swirling bands of radiation that encircle living worlds, our journey now descends into the very heart of stellar mortality. Here, where a star's life draws toward its final curtain, the universe stages one of its most sublime performances. An interplay of brilliance and stillness, of violent energy and solemn quiet. This is not merely the end of a celestial body. It is a cosmic ritual where light explodes into being only to be smothered by silence. In the death of stars, the universe writes its most luminous farewells and its most eternal silences. The life cycle of a star begins in dust and gas, but it ends in fire and collapse. As hydrogen fuel is exhausted in the core, fusion slows and the delicate balance that holds the star in equilibrium begins to fracture. The outward pressure generated by nuclear reactions, which for eons has fought against the crushing inward pull of gravity, falters. Gravity wins, and when it does, it doesn't just draw the curtain, it tears it down. Depending on its mass, a star's death can take several forms, each marked by a distinctive choreography of light and silence. Low-mass stars like our Sun die quietly, shedding their outer layers in slow, ghostly pulses, leaving behind a white dwarf, an ember of stellar memory. These planetary nebulae, as they are called, expand into space like cosmic jellyfish, glowing faintly as a rain, as clustered glacier, from crimson, as yellow for far and crimson. For a time, these structures radiate with beauty, illuminating the stellar corpse within. But eventually the light dims, the gas disperses, silence returns. The white dwarf cools, dimming over billions of years into a black dwarf, a body so inert it becomes indistinguishable from the dark it occupies. But massive stars take another route. Their deaths are anything but quiet. When iron accumulates in their cores, a substance fusion cannot further transform, the energy balance collapses catastrophically. In a fraction of a second, the core implodes. Then, in one of nature's most violent acts, a shockwave blasts outward, tearing the star apart in a supernova. This is among the brightest events in the universe. One star, for a brief time, can outshine an entire galaxy. Light pours across the cosmos, carrying with it the chemical legacy of the star. Carbon, oxygen, silicon, iron, and beyond. Elements that will one day seed new stars, planets, and perhaps even life. Yet, even in this supreme act of brightness, silence is not banished. The light may travel, but the sound does not. The explosion, though unimaginably powerful, makes no noise in the vacuum of space. In earthly terms, a supernova is utterly silent. Its thunder never heard beyond the star it destroys. The remnants of the explosion form expanding shells of gas, called supernova remnants. Structures like the Crab Nebula, which still glows with the energy of a star that died 1,000 years ago, yet continues to radiate long after the world that saw it has turned. Some stellar corpses are more extreme. When the mass of the remaining core exceeds certain limits, gravity crushes the material into neutron stars, city-size objects so dense that a single teaspoon of their matter would weigh billions of tons. These neutron stars often become pulsars, spinning rapidly and emitting beams of electromagnetic radiation that sweep the cosmos like lighthouse beacons. With each rotation, a flash of light pierces the dark, perfectly timed, perfectly precise. These are the heartbeats of stars long dead, echoing through space with mechanical clarity. Their rhythm is real, but their sound remains absent. They pulse in silence, governed by the laws of physics, but shrouded in the hush of the void. And in even rarer cases, the collapse is total. Nothing, not even neutron pressure, can resist the gravitational onslaught. A black hole is born. This is not just death, it is disappearance. The event horizon forms, a boundary from which not even light can escape. No more radiation, no more visible trace. A star that once outshone entire clusters vanishes into darkness. Yet the silence that follows is not the absence of meaning, but the presence of unknowable mystery. The black hole does not announce its birth with sound or fury. It simply ceases to communicate, drawing light, time, and space itself into a gravitational stillness. Yet even in this ultimate quiet, traces remain. Surrounding black holes, matter swirls into a accretion disk. Hot, bright, chaotic. Jets of plasma can erupt from the poles, traveling at nearly the speed of light. Gravitational waves ripple outward when two black holes merge, warping the very fabric of space-time in a silent scream, detectable only with the most sensitive instruments. The end of a star is thus never truly an end. It is transformation, it is scattering and compression, radiation and darkness, silence and energy fused in cosmic contradiction. From these stellar deaths, the seeds of future generations are sown. The heavy elements forged in supernovae are swept into interstellar space, mixing with clouds of hydrogen and dust. New stars form, new planets condense, life may begin again. Every atom in your body, every carbon in your cells, every calcium in your bones, every iron in your blood was born in the heart of a dying star. The light and silence of stellar death live on in us. This paradox, that death begets creation, that silence coexists with energy, defines the cosmic order. The universe is not built solely on explosions and fire, nor on cold emptiness alone. It is shaped by the dialogue between both. And in this dialogue, we hear the voice of time itself. As we near the final edge of this journey, we cast our gaze toward the most distant and enigmatic messengers of the cosmos, quasars. These ancient powerhouses, screaming across the void from the dawn of time, are the loudest voices in a fading universe. In our next chapter, we will confront the blinding brilliance of quasars, where silence is swallowed by light, and time itself glows with the echoes of beginnings too far to touch. Quasars, the loudest voices of the distant past. As we move from the quiet final breaths of dying stars into the vastness of the ancient universe, a paradox greets us. In the earliest epochs, before galaxies matured and stars like our sun were born, there were voices so loud, so powerful, that they could still be heard across billions of light years. These were not voices of sound, but of energy. Blinding radiative fury born in the hearts of young galaxies. They are the quasars. Cosmic lighthouses whose beams pierce the fabric of time, their ancient light still streaming toward us from the edge of the observable universe. The term quasar is short for quasi-stellar radio source, a name born of initial confusion. When astronomers first detected them in the mid-20th century, quasars appeared star-like in optical telescopes, but emitted massive amounts of radio waves, something ordinary stars do not do. The first of these mysterious objects, 3C273, revealed that it lay far beyond our galaxy. It was a revelation. Something so small in appearance, yet so distant and so luminous, had to be fueled by unimaginable power. We now know that quasars are the blazing cores of young galaxies, powered by supermassive black holes consuming matter at astonishing rates. At the heart of every quasar lies a black hole, millions to billions of times the mass of our Sun. Yet it is not the black hole itself that shines. It is the accretion disk of gas, dust and stellar debris spiraling into oblivion that radiates with such intensity. As matter falls inward, gravitational energy is converted into heat and light. The friction within this maelstrom is so great that it produces temperatures hotter than the centers of stars. Quasars outshine their host galaxies, by factors of hundreds, sometimes thousands. In this sense, quasars are both destroyers and illuminators. They consume matter but emit light. They are symbols of entropy and energy simultaneously. They are where silence meets its greatest challenge, the roar of radiation so vast it travels across time itself. For the light we observe from quasars today was emitted when the universe was a fraction of its current age. Some quasars we see now shone forth less than 1 billion years after the Big Bang. Their light has been crossing space ever since, carrying with it messages from an era before Earth existed, before the Milky Way had fully formed. But quasars do not last forever. Their brilliance is a sign of a feeding frenzy, not of permanence. Once the black hole exhausts its surrounding material, the light fades. The galaxy remains and the black hole persists. But the quasar is gone. Thus, quasars are markers of a specific phase in galactic evolution. Youthful exuberance followed by mature quiet. This pattern mirrors in some cosmic way the lives of stars. A fiery birth, a brilliant prime, and a slow descent into silence. Quasars also serve as tools of cosmic archaeology. Because of their distance, they allow astronomers to probe the early universe. As their light passes through intergalactic space, it is absorbed by gas clouds, leaving fingerprints, absorption lines, that reveal the composition, temperature, and motion of matter billions of years ago. In this way, quasars illuminate not just their own galaxies, but the entire path between them and us. They act as backlights for the universe's structure, exposing the invisible filaments of gas and dark matter that connect galaxies across vast cosmic webs. In terms of energy output, quasars are unmatched. A single quasar can emit more energy in 1 second than our entire solar system will produce in its lifetime. And yet this energy does not explode outward evenly. Quasars often direct their emissions along narrow jets, focused beams of particles and radiation that stream outward at near-light speeds. These jets can stretch for hundreds of thousands of light-years, impacting nearby galaxies, heating gas, and quenching star formation. In this way, quasars do not merely shine. They sculpt. They influence the environments around them, regulating the growth of galaxies and the emergence of stars. Despite their ancient origin, quasars may also hold clues to our future. Some theories suggest that if the universe continues to expand, the only visible objects billions of years from now will be quasars, whose light has taken that long to arrive. In that distant era, civilizations, if any still exist, may gaze up and see a sky dominated not by familiar stars and galaxies, but by the fading echoes of quasars. These glowing remnants would become the last storytellers of a cosmos growing dim. Quasars also invite philosophical reflection. They embody extremes of brightness, distance, time, and power. They are voices from an epoch where the universe was violent and unshaped, yet they tell a tale of order emerging from chaos, of structure rising from a sea of hydrogen and helium. They connect us to the beginning, not just through light, but through the elements they helped distribute, the galaxies they influenced, and the questions they continue to pose. Their very existence challenges our understanding of time. Light from a quasar may take 10 or 12 billion years to reach us, yet we see it now, as if its past is our present. In observing a quasar, we are not merely looking across distance, we are looking across time, peering into a universe that no longer exists in that form. The light has endured, while the source may have long faded into silence. In this way, the cosmos preserves memory through radiation. Silence may come, but it never arrives without a whisper of what once was. As the voices of quasars grow fainter across the cosmic sea, we look toward an even more profound stillness. An absence so total it approaches the cessation of existence itself. What happens to energy, to light, to motion, when the universe can no longer sustain them? In the next chapter, we turn to a realm colder than any we know, a place beyond the reach of radiation, the strange frontier of absolute zero and the absence of radiant energy, where silence is not just a lack of sound, but the absence of becoming. Absolute zero and the absence of radiant energy. The universe, in all its brilliance, has never stopped emitting light, from the blazing fires of the earliest quasars to the soft whisper of the cosmic microwave background. But there exists a theoretical boundary where even this eternal radiation fades, a frontier beyond which matter ceases to move, where atoms fall into complete stillness and photons no longer roam. This is the realm of absolute zero, the coldest temperature allowed by the laws of physics, and in its silent dominion, radiant energy surrenders to the void. To understand absolute zero, one must first revisit the very nature of heat. In the universe, temperature is not a substance. It is motion. It is the kinetic energy of particles, the vibration of atoms, the rotation of molecules. The hotter an object, the more frantically its constituents move. The colder it becomes, the more their motion slows. At absolute zero, 0 Kelvin or negative 460.6 degrees Fahrenheit, all classical motion halts. Particles no longer vibrate. Electrons sink into their lowest possible energy states. Heat, in any conventional sense, is gone. And with heat gone, so too is light. Radiant energy, the kind we observe in infrared, visible, ultraviolet, and other wavelengths, depends on the thermal activity of matter. Every object above absolute zero radiates some form of electromagnetic energy. A glowing star, a warm planet, even a block of ice, all emit light, though much of it may be invisible to the human eye. But at absolute zero, this emission ceases. Without molecular motion, there are no transitions between energy states. No thermal photons are produced. The object becomes a perfect absorber of light, a theoretical construct known as a black body, yet it emits nothing of its own. It is not just dark, it is silent in the language of radiation. In the natural universe, absolute zero is never fully reached, even in the coldest places. Deep interstellar space, the shadows of distant moons or the voids between galaxies, there remains a faint bath of residual heat, mostly from the cosmic microwave background. This leftover glow from the Big Bang ensures that even the darkest void still hums at just a few degrees above absolute zero. It is a low murmur of energy that prevents perfect stillness. Yet, the idea of absolute zero remains crucial. It is the limit that shapes thermodynamic laws, the benchmark for entropy, and the defining edge of what is physically possible. The concept was first articulated in the 17th century, but it wasn't until the rise of quantum mechanics that scientists truly understood its implications. According to quantum theory, even at absolute zero, particles still exhibit zero-point energy, a faint, irreducible twitch born not of heat, but of the quantum uncertainty principle. Thus, while classical motion ceases, quantum fluctuations endure. The universe never becomes completely static. Humanity has come remarkably close to this ultimate stillness. In laboratories on Earth, physicists have cooled atoms to within a fraction of a billionth of a degree above absolute zero. In these exotic states, matter behaves in ways that defy ordinary expectations. At such temperatures, atoms can form a Bose-Einstein condensate, a state of matter where they lose their individual identities and behave as a single quantum entity. These condensates flow without friction, conduct electricity without resistance, and can even slow down beams of light to walking speed. They offer a glimpse into a universe stripped of its usual activity, a hint of what might exist in the farthest future. Beyond the laboratory, absolute zero also haunts the cosmic future. As stars exhaust their fuel and galaxies drift apart under the influence of dark energy, the universe is expected to cool further. Over unimaginable spans of time, radiation will fade, stellar remnants will collapse or evaporate, and black holes will slowly emit Hawking radiation until they too vanish. What remains is a bleak expanse, an era sometimes called the degenerate era, where the universe approaches thermodynamic equilibrium. No new stars will form, no new light will shine. Over even longer scales, all particles may decay, leaving behind a sparse ocean of low-energy photons and neutrinos. The universe, though still expanding, will become dark, cold, and quiet. In this final age, the cosmos drifts toward absolute zero. Radiant energy, once so abundant, will be reduced to a background so faint it borders on the undetectable. The silence of this future will not be metaphorical, it will be literal, carved into the very laws of physics. This is the logical endpoint of entropy's rule, a state of maximum disorder and minimal energy, where the ability to perform work vanishes and all processes halt. It is the universe's ultimate stillness. But even here, in this frozen expanse, questions remain. Will quantum fluctuations spark new realities? Will dark energy itself transform into something else? Could the universe rebound in a cyclical model, birthing a new cosmos from the ashes of the old? Or is absolute zero the true finale, a cold tomb sealing the last chapter of creation? What began with the fierce roar of the Big Bang ends in a breathless whisper, and eventually in silence complete. The story of radiation, the story of the cosmos itself, is one of emergence, evolution, and eventual extinction. But within that story, a final paradox arises. In the march toward absolute silence, life once emerged, brilliant and brief, as a voice in the darkness. And so, as we prepare to conclude this exploration of cosmic radiation and silence, we must ask, what remains when the light is gone, when the fire has cooled, and when silence finally reigns without rival? The answer may lie in the next and final chapter of our journey, where the stars no longer shine, the galaxies no longer spin, and the future belongs not to what is, but to what is absent. In the closing act, we confront future silence, the fading of cosmic light. Future, silence, the fading of cosmic light. In the beginning, there was light, not merely the light of stars or the fire of galaxies, but the very birth cry of the cosmos. Pure radiation exploding into space from a point beyond comprehension. From that singular genesis emerged every particle, every atom, every spark of energy that would ever exist. Over time, light flooded the universe, not just illuminating the dark, but sculpting it, giving it form, meaning, and direction. But what if this light, so essential to our understanding of space, time, and ourselves, is not eternal? What if the universe is quietly heading toward a final, inevitable silence? Not the silence of void, but the absence of light itself. That is the path we now trace, a journey not through what is, but what is ceasing to be. The fading of cosmic light is not sudden. It is not dramatic. It is gradual, glacial, and inevitable. And it begins now, even as stars still burn, galaxies still shimmer, and quasars still whisper from the farthest reaches of space. To grasp this future silence, we must understand the life cycle of light. Every star that burns is a temporary machine of fusion, transforming mass into energy. That energy radiates across the electromagnetic spectrum, visible, infrared, ultraviolet, X-ray, gamma. For billions of years, stars have been the engines of light, turning hydrogen into helium, helium into heavier elements, and casting illumination into the black. But even stars have limits. Fuel is not infinite. The forces that once ignited them also ensure their eventual collapse. Already, many stars have died. Some have become white dwarfs, small, dense, cooling embers of once bright giants. Others have turned into neutron stars, or even vanished into black holes. These remnants persist, but they do not shine as they once did. They glow faintly, shedding their remaining heat into space. Over trillions of years, even these last lights will dim. White dwarfs will become black dwarfs, hypothetical objects so cold and dark they emit no detectable energy. Neutron stars may evaporate or drift, their once mighty pulses silenced. The cosmos will grow quieter, not in sound, but in radiation. Galaxies too will wither. The spiral arms that once burst with star formation will go still. Gas clouds that once seated stellar nurseries will be exhausted or stripped away. The birth rate of stars will drop to near zero. Collisions between galaxies, once violent and luminous, will continue, but without fresh material, they will produce no new radiance. Black holes at galactic centers will continue to feed for some time, lighting quasars for a while longer, but eventually even these will go dark. And then, over unfathomable stretches of time, the last stars will flicker out. The universe will be left to its remnants: black holes, cold white dwarfs, frozen neutron stars, and vast seas of lonely particles, their motions governed only by gravity and decay. Yet even black holes will not endure forever. According to Hawking radiation, these seemingly eternal prisons of light will, over eons, evaporate particle by particle. It is a slow death, a trickle of energy, released from the very fabric of space near their event horizons. The largest black holes will take unimaginable lengths of time to disappear, but they too will vanish. When the final black hole emits its last quantum of heat, an epoch will end. This long twilight is sometimes called the Dark Era. But even that term is generous, for darkness suggests contrast, shadow against light. In this future there will be no light left for contrast. No sunrises, no starlight, no quasars burning across the sky, just a cosmic silence of radiation. Only low-energy photons, stretched by the ever-expanding fabric of the universe, cooling to near nothingness. A diffuse sea of residual warmth, too faint to illuminate, too soft to feel. In this far-flung future, entropy reigns supreme. The universe approaches its maximum disorder, a state of thermodynamic equilibrium. No energy gradients remain to drive processes. no work can be done. This is not a cosmic catastrophe. It is the natural end of a system governed by the second law of thermodynamics. The universe does not end in a bang or a blaze, but in coldness. And yet, this fading is not without meaning. The light that once was still echoes in the relics of radiation. The cosmic microwave background remains as a fossil of the Big Bang. Light from distant galaxies still travels, even if those galaxies are long dead. Photons released 1 trillion years ago may still be in flight, crossing space too vast to comprehend. They are the messengers of what once was, persistent beyond their origin. In this way, the silence of the future is not entirely mute. It holds within it the memory of sound. It is not blankness, but legacy. Every star that lived, every planet that reflected light, every supernova that flared and faded, they all left imprints in the fabric of space-time. The absence we face is carved from the presence that came before. For humanity, this realization is both humbling and profound. We live in an age of light. We orbit a star in its prime. We observe galaxies at their brightest and measure the early universe through ancient photons. We exist in a moment when radiation still reigns, but we know this moment is temporary. Cosmic light is not an eternal flame. It is a candle in a darkening room. And yet, perhaps there is hope in that recognition. Perhaps by knowing the finite nature of cosmic illumination, we find reason to cherish it, to explore it, to understand it, to use it not just for science, but for meaning. The universe is fading, yes, but it has not yet faded. The silence has not yet fallen. The stars still speak, the light still travels. In the end, the story of radiation and silence is the story of balance. The balance between energy and emptiness, between order and entropy, between being and becoming. It is the story of the universe itself, told not in words, but in wavelengths, in silence and in light. And as long as one photon still moves through space, as long as one eye still sees, that story continues. So we end where we began, with the voice of the cosmos. A voice of fire, of fusion, of collapse and echo, and with the silence that waits, not as an end, but as a continuation. A space for memory, a place for possibility, a stillness that holds all the light that ever was. In the vast, ever-expanding frontier of human exploration, there exists a journey so awe-inspiring and monumental that it transcends the very boundaries of time and space. This epic voyage is none other than the extraordinary odyssey of Voyager 1, a pioneering spacecraft launched by NASA that has traveled farther than any other human-made object, carrying the hopes and dreams of humanity into the deepest reaches of the cosmos. Recently, Voyager 1 sent back a historic transmission to Earth that has ignited waves of excitement and curiosity throughout the global scientific community and beyond. At the heart of this remarkable message lies a discovery of unparalleled significance, an enigmatic object detected in the profound, uncharted depths of interstellar space. This mysterious revelation has reignited one of the most timeless and compelling questions that has captivated humanity for generations. Could this signal represent the long-awaited moment when we finally establish contact with advanced extraterrestrial life? For centuries, humankind has gazed up at the night sky with wonder, imagining the possibility of other civilizations thriving among the stars. Now, this revelation has brought those age-old dreams tantalizingly close to reality. Voyager 1's journey began decades ago when it was launched on September 5, 1977, as part of NASA's ambitious Voyager program. Its mission was bold and profound: to act as Earth's emissary, venturing beyond the familiar realms of our solar system into the vast unknown, while meticulously studying the outer planets and their moons. Voyager 1's remarkable voyage was marked by a serendipitous cosmic alignment. It set off just 16 days before its twin, Voyager 2, beginning a cosmic ballet that has unfolded for more than 40 years. What truly sets Voyager 1 apart from countless other space missions is its extraordinary spirit of communication. Despite its unfathomable distance from Earth, Voyager 1 maintains a steadfast dialogue with our home planet through NASA's venerable deep space network. This complex and powerful communication system allows Voyager 1 not only to receive commands, but also to transmit back invaluable streams of scientific data, bringing us ever closer to understanding the cosmos. As of the latest measurements, Voyager 1 is an astonishing 159.32 astronomical units AU away from Earth, equivalent to nearly 23.8 billion kilometers, or approximately 14.8 billion miles. This staggering distance makes it the most distant human-made object ever to voyage into space. Yet, despite this incredible remoteness, Voyager 1's instruments continue to operate, tirelessly collecting and sending back information that deepens our understanding of the universe around us. Voyager 1's primary mission was to explore the outer boundaries of the heliosphere, the vast bubble of charged particles and magnetic fields generated by the Sun. This outer boundary, called the heliopause, marks the frontier where the influence of our star gives way to the cosmic environment of interstellar space. Crossing this threshold in 2012, Voyager 1 became the first human-made object to enter the space between stars, beginning a new chapter in space exploration. What makes Voyager 1's mission truly remarkable is not only its groundbreaking discoveries, but also its extraordinary endurance. Originally designed to last only a few years, Voyager 1 has surpassed all expectations, continuing its interstellar journey for over 4 decades. Each day, it cruises through the void at an incredible speed of approximately 38,000 miles per hour, sending precious data back to Earth across billions of miles. Scientists anticipate that Voyager 1 will continue this historic mission at least until 2025, when its power sources are expected to diminish. Equipped with a sophisticated suite of 10 scientific instruments, including cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, cosmic ray sensors, and radio science equipment, Voyager 1 was built to be humanity's eyes and ears in the cosmos. These instruments have enabled the spacecraft to withstand the harsh and unforgiving conditions of deep space, while delivering an unprecedented wealth of knowledge about the outer solar system and beyond. Among Voyager 1's most celebrated achievements are its close flybys of 2 colossal gas giants, Jupiter and Saturn. In 1979, Voyager 1 made its first close approach to Jupiter, revealing breathtaking details about the planet's turbulent atmosphere, intricate ring system, and diverse moons. The spacecraft's instruments confirmed the existence of faint rings around Jupiter, previously only theorized, and uncovered previously unknown moons that added to our understanding of the planet's complex environment. A year later, in 1980, Voyager 1's encounter with Saturn provided equally stunning insights. It unveiled the intricate structure of Saturn's iconic rings, captured detailed images of its moons, and deepened our knowledge of the planet's magnetic field and atmosphere. These flybys not only revolutionized planetary science, but also inspired a new generation of explorers, scientists, and dreamers around the world. One of the most iconic moments in Voyager 1's journey came in 1990, when the spacecraft, prompted by the visionary astronomer Carl Sagan, turned its cameras back toward Earth and captured the now famous image known as the pale blue dot. In this extraordinary photograph, Earth appears as a tiny speck suspended in a vast cosmic ocean, a fragile and precious home floating in the immense void of space. This image remains a powerful symbol of humanity's shared vulnerability and interconnectedness, reminding us of the urgent need to cherish and protect our only home. As Voyager 1 continues its silent journey through the darkness beyond our solar system, it carries with it the legacy of human curiosity, ingenuity, and the unquenchable desire to explore. Its latest discovery in the depths of interstellar space hints at new cosmic mysteries waiting to be unveiled, perhaps even the momentous encounter with other life forms that so many have dreamed about. This odyssey, which began over 4 decades ago, continues to inspire and challenge us, inviting us all to look up, wonder, and reach ever further into the vast expanse of the universe. Voyager 1 was designed to push the boundaries of human knowledge, traversing vast distances where no spacecraft had dared to go before. Equipped with a suite of sophisticated scientific instruments, it was tasked with studying the giant planets and their moons, capturing unprecedented data that would forever change our understanding of the solar system. What makes Voyager 1 truly extraordinary is not just its groundbreaking discoveries, but its resilience and longevity. Despite being launched over 4 decades ago, it continues to send invaluable information back to Earth, maintaining a lifeline of communication through NASA's Deep Space Network. This unwavering connection allows scientists to receive data from more than 14 billion miles away, a testament to human ingenuity and determination. As Voyager 1 journeys beyond the heliosphere, the protective bubble created by the Sun's solar wind, it enters interstellar space, a vast expanse filled with cosmic mysteries. Recently, a signal from Voyager 1 revealed the detection of an enigmatic object lurking in this farthest frontier. This revelation has sent shockwaves through the scientific community and reignited a question that has fascinated humanity for generations. Are we alone in the universe? The possibility that this mysterious detection could be evidence of advanced extraterrestrial life has captivated imaginations worldwide, inspiring scientists, philosophers, and dreamers alike to ponder the cosmic significance of this discovery. As we delve deeper into Voyager 1's findings, we are reminded of the boundless curiosity that drives human exploration, our relentless quest to understand not only the universe, but our place within it. In this unfolding cosmic saga, Voyager 1 stands as a symbol of hope, perseverance, and the unquenchable thirst for knowledge. Its voyage is not merely a scientific endeavor, but a profound journey that connects us all, uniting humanity in awe of the infinite cosmos that stretches beyond our wildest dreams. An intriguing aspect of the Voyager mission narrative lies in the remarkable timing. Voyager 1 began its epic journey just 16 days ahead of its cosmic twin, Voyager 2. This serendipitous alignment lends a sense of cosmic symmetry to an unparalleled saga. 2 intrepid emissaries of humanity launched in close succession, each destined to explore the uncharted realms of our solar system and beyond. What truly distinguishes Voyager 1 from countless other space missions is its indomitable spirit of communication, a lifeline that it maintains steadfastly with Earth across unimaginable distances. This extraordinary feat is made possible by NASA's venerable Deep Space Network, a robust and sophisticated communication infrastructure designed to ensure a constant dialogue between the spacecraft and its home planet. This unyielding link serves a dual purpose. It allows Voyager 1 to receive precise commands from mission control and, in return, to transmit a treasure trove of invaluable scientific data back to its terrestrial origins. According to the most recent data, Voyager 1 currently finds itself at an astonishing distance of approximately 159.32 astronomical units (AU) from Earth. To put this monumental achievement into perspective, this distance translates to an awe-inspiring 23.834 billion kilometers, or roughly 14.8 billion miles, away from the cradle of humanity. In other words, Voyager 1 is now the most distant human-made object in existence, a lone traveler venturing farther into the cosmic ocean than any other craft before it. This staggering remoteness not only speaks to the spacecraft's incredible durability and the brilliance of human engineering, but also marks a milestone in our quest to understand the universe around us. It is this incomprehensible remoteness that firmly establishes Voyager 1 as the most distant human-made object ever to embark on an odyssey into the vast cosmos. From the moment of its launch, Voyager 1's primary mission objective was clear and profoundly ambitious: to explore and meticulously scrutinize the boundaries of the outer heliosphere, a mysterious and barely understood region known as the heliopause. This invisible boundary marks the outermost layer of the Sun's influence, the final frontier where the solar wind meets the vast interstellar medium, enveloping our entire solar system in a protective bubble. Through its relentless investigations, Voyager 1 has bestowed humanity with invaluable insights into the cosmos, especially within the confines of our immediate solar neighborhood. Propelled forward at an astonishing velocity of approximately 38,000 miles per hour, an incredible speed that allows it to traverse vast cosmic expanses day by day, the spacecraft continues to push the boundaries of exploration and knowledge. Yet, what truly sets Voyager 1 apart is not just its distance or speed, but its remarkable endurance. The spacecraft has not merely met expectations, it has far exceeded its originally projected lifespan. More than 4 decades after its historic launch, Voyager 1 remains operational, tirelessly sending back vital data from the farthest reaches of space. Its ongoing mission serves as a testament to human ingenuity, perseverance, and an insatiable desire to understand the universe around us. Voyager 1 has embarked on extraordinary decades of exploration, defying the limits of time and technology. Each passing day, this remarkable spacecraft dutifully records and transmits vital information about its celestial journey, offering humanity a continuous stream of priceless data from the edge of our solar system and beyond. Remarkably, Voyager 1 is expected to continue this awe-inspiring interstellar sojourn until at least the year 2025, a testament to its resilient propulsion systems and enduring power supply that have kept it operational far beyond initial expectations. By that time, it is estimated that Voyager 1 will have achieved an almost inconceivable distance of approximately 13.8 billion miles from the nurturing embrace of the Sun, a staggering measure of its pioneering voyage into the cosmic unknown. Accompanying Voyager 1 on this grand adventure is its celestial sibling, Voyager 2, both launched as part of NASA's legendary Voyager program. Together, they were equipped with a formidable array of 10 unique scientific instruments, each serving as sensory extensions of the spacecraft into the vast cosmos. This sophisticated ensemble of tools included television cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, cosmic ray and charged particle sensors, as well as state-of-the-art radio equipment, all meticulously designed to conduct groundbreaking experiments. These ingenious instruments have endowed Voyager 1 with the resilience and capability to withstand the harsh and unforgiving environs of deep space, allowing it to probe the unfathomable reaches of the unknown. One of the most indelible milestones in Voyager 1's storied journey was its close encounters with two of the most majestic and enigmatic bodies in our solar system, Jupiter and Saturn. These historic flybys provided humanity with an unprecedented window into the complexities and wonders of these gas giants, forever reshaping our understanding of the planetary giants and their moons. Voyager 1's encounters with the solar system's colossal planets, Jupiter and Saturn, were nothing short of historic. These celestial rendezvous, which occurred in 1979 and 1980, respectively, marked a watershed moment in the annals of scientific discovery. Through these close flybys, Voyager 1 gifted humanity with an unprecedented glimpse into the intricate complexities of these gas giants and their enigmatic retinues of moons. The spacecraft etched its name indelibly into history by uncovering previously unknown moons orbiting these planets, and by revealing the intricate and delicate ring structures that encircled both Jupiter and Saturn. Prior to Voyager 1's mission, much of this was speculation or incomplete knowledge. Its groundbreaking revelations not only captivated the scientific community, but also ignited the imaginations of people across the globe, heralding a new era of planetary exploration. One of Voyager 1's most iconic and enduring contributions to our cosmic understanding came in 1990 when the celebrated astronomer Carl Sagan championed a visionary concept. He urged the spacecraft to pivot its cameras and direct its lens back towards Earth. This simple yet profound act resulted in the creation of the now famous image known as the pale blue dot. The resulting image, now deeply etched into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant image serves as a humbling reminder of the fragility and interconnectedness of our planet, underscoring the imperative to cherish and protect our world. A message that continues to resonate powerfully with people around the globe. Voyager 1's epic journey through the cosmos led it to encounter two of the most enigmatic and majestic celestial bodies in our solar system, Jupiter and Saturn. These monumental encounters provided a treasure trove of scientific data and imagery, fundamentally reshaping our understanding of these gas giants. Jupiter, the largest planet in our solar system, beckoned Voyager 1 with its beguiling mysteries. In March 1979, the spacecraft conducted a close flyby of this colossal giant, granting humanity its first intimate glimpse of the planet's immense scale and complexity. As Voyager 1 ventured closer, it unveiled a tapestry of astounding discoveries, one of the most captivating being the confirmation of Jupiter's intricate ring system. Before Voyager 1's arrival, these faint rings were only a hypothesis, but the spacecraft's keen instruments provided definitive evidence of their existence. Composed of fine, dark particles, these delicate rings encircle Jupiter in an ethereal fashion. The images captured by Voyager 1 offered an entrancing perspective on this subtle feature, captivating the world with their delicate beauty and adding a new dimension to our cosmic knowledge. Another remarkable revelation from Voyager 1's encounter with Jupiter was the unveiling of intricate weather patterns and tempestuous storms on the gas giant's surface. Among these tempests, the most iconic was the Great Red Spot, a colossal storm that has raged for centuries. Voyager 1's imagery of this mammoth tempest not only illuminated the storm's complex structure and dynamic behavior, but also ignited the public's fascination with Jupiter's tumultuous atmosphere. Furthermore, Voyager 1's instruments detected Jupiter's powerful magnetosphere, a colossal magnetic field that dwarfs Earth's own magnetic envelope. This groundbreaking discovery provided crucial insights into the planet's magnetic dynamo and shed light on how this immense magnetic field interacts with its retinue of moons, influencing their environments and contributing to the complex space weather around Jupiter. Following its momentous encounter with Jupiter, Voyager 1 continued its epic odyssey toward Saturn, the majestic ringed planet. In November 1980, the spacecraft made its closest approach to this cosmic wonder, offering humanity an intimate view of Saturn's stunning rings and captivating moons. The detailed images and data collected unveiled previously unseen features of the rings' delicate structure and composition, as well as the diverse geology and atmospheres of Saturn's many moons. One of Voyager 1's most iconic contributions to human perspective came in 1990 with the celebrated pale blue dot image. The esteemed astronomer Carl Sagan championed a visionary idea. He implored the spacecraft to pivot its cameras and turn its lens back toward Earth. This image immortalized our planet as a tiny, fragile speck suspended in the vastness of space, inspiring reflection on our place in the cosmos and a renewed commitment to safeguarding our shared home. The resulting image, now etched deeply into the collective consciousness of humanity, depicts Earth as a minuscule pale blue dot suspended in the vast cosmic ocean. This poignant and humbling image serves as a powerful reminder of the fragility, vulnerability, and profound interconnectedness of our planet within the boundless expanse of the universe. It underscores the urgent imperative to cherish, protect, and preserve our delicate home, a message that continues to resonate with people from all corners of the globe, inspiring reflection on our shared responsibility to safeguard life on Earth. While Voyager 1's extraordinary odyssey primarily focused on the majestic gas giants Jupiter and Saturn, its twin spacecraft, Voyager 2, embarked on a distinct and equally remarkable trajectory. Voyager 2 was destined to explore the enigmatic ice giants of our solar system, Uranus and Neptune, planets shrouded in mystery and complexity, presenting a fresh array of cosmic enigmas for scientists and humanity to unravel. Uranus, the seventh planet from the Sun, is a celestial enigma for many reasons, not least of which is its extraordinary rotation. Unlike any other planet in our solar system, Uranus rotates on its side, with an axial tilt of approximately 98 degrees. This unusual orientation is believed to be the aftermath of a colossal and cataclysmic collision with a massive celestial object in the distant past, which drastically altered the planet's spin. This tilt results in extreme seasonal variations lasting over decades, offering a unique glimpse into planetary dynamics that differ greatly from those of Earth and its planetary neighbors. Despite its unusual tilt and mysterious origins, Uranus remains a captivating and fascinating world. It is approximately 4 times the diameter of Earth and boasts a cold, icy atmosphere composed mainly of hydrogen, helium, and methane, giving it a characteristic blue-green hue. Voyager 2's historic flyby of Uranus in January 1986 marked a momentous milestone in space exploration. For the first time, humanity received detailed images and comprehensive scientific data of this distant ice giant, expanding our knowledge far beyond previous telescopic observations. Among the many groundbreaking discoveries during Voyager 2's encounter was the revelation that Uranus possesses a complex system of rings, a surprising finding since rings were once thought to be unique to Saturn. Voyager 2 revealed that these rings consist of dark, narrow bands composed of tiny particles and debris orbiting the planet, hinting at dynamic processes within Uranus's gravitational influence. In addition to its rings, Voyager 2 discovered 10 new moons orbiting Uranus, each with its own unique characteristics and geological histories. The spacecraft's instruments also provided valuable insights into the planet's atmosphere, uncovering high-speed winds and unexpected temperature variations that challenged existing models of planetary atmospheres. These findings offered a new window into the workings of ice giants, enriching our understanding of planetary formation and behavior in the outer solar system. Voyager 2's journey did not end with Uranus. It continued onward to Neptune, the outermost planet in our solar system, arriving in August 1989. Neptune, with its striking deep blue color and fierce weather systems, presented yet another frontier of exploration and discovery. The data and images sent back by Voyager 2 from Neptune's vicinity revealed powerful storms, supersonic winds, and a moon with active geysers. An astounding discovery that further deepened our appreciation for the dynamic complexity of these distant worlds. Together, the twin Voyager spacecraft have revolutionized our understanding of the solar system's outer realms. Their pioneering missions, spanning more than 4 decades, have transformed once faint and distant dots in the night sky into vividly detailed worlds, full of mystery and wonder. These missions continue to inspire generations of scientists, dreamers, and explorers, reminding us that even at the very edges of human reach, the universe holds countless secrets waiting to be discovered. Voyager 2 revealed a diverse and captivating retinue of moons orbiting Uranus, each possessing unique geological and atmospheric features. Among these, moons like Miranda, Ariel, and Titania stood out, showcasing dramatic landscapes marked by massive canyons, unusual fault lines, and evidence of past geologic activity. These discoveries significantly enriched humanity's understanding of Uranus, shedding light on the complex interactions between the planet and its satellites, and deepening the intrigue surrounding this enigmatic, sideways rotating giant. Voyager 2's interstellar voyage did not end at Uranus. It pressed onward, journeying even farther to reach Neptune, the 8th and most distant known planet from the Sun. Neptune, with its frigid temperatures and vibrant azure hue, remains a haunting symbol of the solar system's outer frontier. This distinct blue coloration is due to the high concentration of methane in its atmosphere, which absorbs red light and reflects the blue. In August 1989, Voyager 2 conducted a historic flyby of Neptune, marking the first, and so far only, close encounter with this distant world. The images and data transmitted back to Earth during this flyby were nothing short of revolutionary. Voyager 2 unveiled a planet with a surprisingly dynamic atmosphere, teeming with violent storms and fierce winds, the fastest sustained winds recorded in the solar system, reaching speeds of over 2,000 kilometers per hour, about 1,200 miles per hour. Among Neptune's most notable atmospheric features was the discovery of the Great Dark Spot, a colossal storm system reminiscent of Jupiter's famous Great Red Spot. However, unlike its Jovian counterpart, the Great Dark Spot proved to be ephemeral. It mysteriously vanished in later observations, raising questions about the atmospheric dynamics of Neptune and the transient nature of its weather system. Perhaps one of the most astonishing revelations from Voyager 2's Neptune encounter was the discovery of the planet's largest moon, Triton, to be an exceptional celestial body that defied expectations. Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction of Neptune's rotation. A rare trait that strongly suggests Triton is a captured object, possibly a former Kuiper Belt object that was gravitationally ensnared by Neptune in the distant past. Triton's surface was revealed to be a frozen yet geologically active world, exhibiting nitrogen geysers erupting from beneath its icy crust, a phenomenon never before observed on a celestial body so distant from the Sun. This cryovolcanic activity indicated that Triton, despite its remoteness and frigid temperatures, harbors internal heat and dynamic processes beneath its surface. Voyager 2's images showed a landscape marked by frozen plains, ridges, and sparsely cratered terrain, suggesting a young and possibly evolving surface. These groundbreaking discoveries at Neptune and Triton not only captivated the global scientific community, but also sparked the imaginations of people around the world. The Voyager 2 mission demonstrated the boundless potential of human curiosity and ingenuity, reminding us that even the most remote and mysterious corners of our solar system can be brought into the realm of human understanding. Voyager 2's historic flybys of Uranus and Neptune marked the end of humanity's first grand tour of the outer planets. A monumental chapter in the annals of space exploration, yet, like its twin Voyager 1, Voyager 2 continues to voyage beyond the known, transmitting faint whispers of data from the edge of interstellar space, ensuring that its legacy endures not just in scientific discovery, but in the shared human spirit of exploration. Triton, the largest moon of Neptune, emerged as one of the most fascinating and enigmatic celestial bodies encountered during Voyager 2's interplanetary odyssey. The spacecraft's imagery revealed a world brimming with activity, despite its remote location and frigid climate. Among Triton's most extraordinary features were geysers that erupted from beneath its icy surface, spewing nitrogen gas high into the moon's thin atmosphere. These geysers created vast plumes that extended kilometers above the surface, where the nitrogen would condense into snow-like particles and gently settle back to the ground, sculpting a surreal and alien landscape of frost and ice. This striking phenomenon was unlike anything previously observed in the solar system, offering profound insights into cryovolcanism, the eruption of volatile substances like water, ammonia, or methane, rather than molten rock. Triton's surface, relatively young and sparsely cratered, hinted at a geologically active history, defying expectations for a moon so far from the Sun. Perhaps even more puzzling was Triton's retrograde orbit. It revolves around Neptune in the direction opposite to the planet's rotation. This uncommon trait strongly suggests that Triton did not form alongside Neptune, but was instead a captured object, likely originating from the Kuiper Belt. Its gravitational capture would have disrupted Neptune's original satellite system and left Triton locked in a stable but unusual orbital dance, one that continues to intrigue astronomers to this day. Voyager 2's encounters with Uranus and Neptune remain unparalleled achievements in the history of space exploration. To this day, no other spacecraft has visited these distant ice giants, making Voyager 2's observations and data collection an irreplaceable scientific treasure. The trove of information gathered during these historic flybys continues to fuel research and hypotheses, offering glimpses into the atmospheric dynamics, magnetic fields, ring systems, and unique satellite compositions of these mysterious worlds. While Voyager 2 was delving into the secrets of the outer planets, its twin, Voyager 1, was forging an even more audacious path, a journey that would take it beyond the boundaries of the solar system and into interstellar space. This transition, which occurred in August 2012, marked a profound and historic milestone for humanity. For the first time, a human-made object had crossed the heliopause, the boundary where the solar wind yields to the interstellar medium. Voyager 1's entry into interstellar space did not signify the end of its mission, but rather the beginning of a new chapter. As it continues its voyage through the vast and silent reaches of the cosmos, it carries with it not only scientific instruments, but also a symbolic message from Earth, etched in the form of the Golden Record, a phonograph disc containing sounds, music, and greetings from our planet. Now billions of miles from Earth, Voyager 1 operates in a realm beyond the Sun's influence, where the environment is dominated by particles, fields, and forces that originate from other stars. Its instruments, though fewer in number now, continue to return invaluable data about the nature of interstellar space, helping scientists to understand the shape and boundary of the heliosphere and the conditions in the space between the stars. The enduring journey of the Voyager spacecraft, Voyager 1, venturing outward into the galaxy, and Voyager 2, providing the only close-up views of Uranus and Neptune, remains one of the most ambitious and successful missions in the history of space science. They have not only expanded the boundaries of human knowledge, but have also inspired generations to look upward and dream of what lies beyond, gathered groundbreaking data that challenged earlier assumptions and reshaped our understanding of this mysterious frontier. Rather than a simple comet-like structure with a long tail trailing away from the Sun, Voyager 1's measurements suggested that the heliopause is more complex, possibly a distorted bubble-like shape influenced by both the solar wind from within and interstellar forces from beyond. As Voyager 1 crossed this boundary in 2012, it recorded a sudden and lasting drop in solar particles, while simultaneously detecting a surge in galactic cosmic rays, energetic particles that originate from supernovae and other powerful cosmic phenomena far outside our solar system. This was the smoking gun, clear empirical evidence that the spacecraft had exited the heliosphere and entered the vast ocean of interstellar space. Within this realm, Voyager 1's instruments continued to function, albeit in a limited capacity due to the fading power supply and increasing distance. Even so, its plasma wave subsystem detected a persistent background hum, long, low-frequency vibrations in the plasma of interstellar space. This discovery provided an unprecedented glimpse into the density and behavior of particles between the stars, and demonstrated that the void of space is, in fact, filled with subtle and dynamic forces. Voyager 1's ongoing mission in interstellar space is a testament to both technological resilience and scientific ambition. It represents the first time humans have been able to directly measure the environment of interstellar space, rather than relying solely on telescopes or theoretical models. The data sent back by Voyager 1 continues to challenge assumptions and refine our models of how the Sun interacts with the galaxy around it. As it sails farther into the unknown, Voyager 1 is also pushing the limits of communication. Its faint signals traveling at the speed of light now take over 22 hours to reach Earth. Each byte of data is a time capsule, whispering stories from the edge of the solar system to a waiting world. Despite being over 46 years old, the spacecraft continues to surprise. In recent years, engineers have performed innovative workarounds to keep it operational, including rerouting functions through backup systems. These efforts ensure that even in its twilight years, Voyager 1 remains a pioneer, a silent emissary of Earth, drifting among the stars. Its journey into interstellar space is not just a scientific achievement, but a symbolic one. Voyager 1 carries the golden record, a carefully curated message intended for any intelligent life that might one day encounter it. Engraved with greetings in 55 languages, music from cultures across the Earth, and images depicting life on our planet, the golden record serves as humanity's cosmic calling card, a whisper to the universe saying, "We were here, we reached this far, and we are curious." Voyager 1 is now far beyond the planets, beyond the influence of our star, continuing its voyage in the silence of deep space. It is alone, yet never forgotten. His legacy etched into history, its mission ongoing, and its story inspiring countless new explorers to reach for the stars. These observations from Voyager 1 provided a transformative understanding of the heliopause and its complex relationship with the galactic environment. Prior to Voyager's journey, much of what scientists knew about the heliosphere was theoretical, based on models, simulations, and indirect evidence. But as Voyager 1 approached and eventually crossed the heliopause, it delivered empirical measurements that revolutionized the field. One of the most unexpected discoveries was the behavior of the magnetic field at the boundary. Scientists had expected a sharp shift in the direction of the magnetic field lines as Voyager 1 transitioned from the Sun's influence to the interstellar medium. However, what they observed was a subtle and unexpected continuity. The magnetic field beyond the heliopods remained aligned in a way that puzzled researchers. This anomaly suggested that the heliosphere might not be as sharply defined or as neatly contained as once imagined. Instead, it could be intertwined or blended with interstellar forces in ways that challenge our understanding of the boundary between solar and galactic domains. These deviations hinted at previously unknown interactions between the solar wind and the interstellar magnetic field, painting a far more dynamic and fluid picture of the Sun's outermost frontier. In addition to its findings on magnetic fields, Voyager 1 also measured plasma density in interstellar space. Unlike within the solar system, where plasma is sparse and influenced by solar activity, the interstellar medium was found to be denser, yet cooler and more stable. This provided critical data that helped astronomers refine their understanding of the material that fills the vast regions between star systems. Voyager 1's traversal into and beyond the heliopause did more than just expand the scientific boundaries of astrophysics. It redefined the scale of our solar system. What was once thought to end at the orbit of Pluto, or perhaps Neptune, was now clearly shown to extend tens of billions of kilometers farther. Enveloped in a vast and shifting magnetic bubble, these findings are not merely academic. They have profound implications for future missions and our long-term aspirations for space travel. Understanding the heliosphere's structure is essential for developing technologies that could one day protect human explorers from cosmic radiation as we venture further from Earth. It also helps in mapping the interstellar environment that any spacecraft, robotic or crewed, would encounter as it journeys to the stars. In essence, Voyager 1's study of the heliosphere turned a once theoretical concept into a tangible and measurable structure, revealing it as a living, breathing force field that protects and defines the domain of our Sun. And while many questions remain about its shape, its interaction with the galaxy, and how it evolves over time, Voyager 1 laid the first real footprints on this invisible frontier. It's a testament to human curiosity and engineering that a spacecraft launched in 1977 continues to inform us decades later about regions of space we had never directly touched before. The mission of Voyager 1 not only broadened our understanding of the heliosphere, but also reminded us that exploration, no matter how distant or difficult, brings us closer to the truth of our place in the cosmos. These contrasting environments encountered by Voyager 1 and Voyager 2 as they crossed the heliopause added profound depth to our understanding of interstellar space. Although both spacecraft pierced the boundary that separates the Sun's protective bubble from the galaxy beyond, the variations in local space weather, magnetic field intensity, and particle density between their paths suggested that interstellar space is not uniform. It is a complex and evolving landscape, shaped by both local and galactic forces. Voyager 2's instruments, still fully operational at the time of its heliopause crossing, recorded direct plasma measurements, something Voyager 1 could not do initially due to a malfunction in its plasma instrument. This allowed Voyager 2 to directly confirm the dramatic rise in plasma density beyond the heliopause, complementing the data Voyager 1 had previously inferred using its cosmic ray and magnetic sensors. This corroboration between two different observational methods provided compelling evidence for a denser interstellar medium just outside our solar system. Moreover, the turbulence Voyager 2 encountered, manifested as fluctuating magnetic fields and wave-like plasma interactions, indicated a more chaotic boundary layer. Scientists hypothesize that this may be due to differences in solar wind pressure or local interstellar cloud structures that distort the heliosphere's edge. In contrast, Voyager 1's path appeared to be through a calmer, more sensitive this frontier is to cosmic condition. Together, these findings from both spacecraft are enabling scientists to create the first three-dimensional models of the heliosphere's outer boundary, which help illustrate its shape, behavior, and interaction with the galaxy. These models are crucial not only for understanding our own solar environment, but also for contextualizing the protective magnetic bubbles that might surround other stars, possibly shielding exoplanets from harmful radiation and influencing their potential to host life. In essence, Voyager 1 and Voyager 2, though launched within weeks of each other, have become dual ambassadors to the galaxy, each offering a distinctive lens on the final frontier of our solar system. Their separate experiences highlight that the edge of our solar system is not a fixed wall, but a living, breathing boundary, shaped by the solar wind's strength, the interstellar medium's density, and galactic magnetic fields that we are only beginning to understand. As Voyager 2 continues its journey through this turbulent interstellar zone, it adds more layers to the grand narrative begun by its twin. Together, they are charting a realm never before visited by humankind. And in doing so, they remind us that even at the edges of our influence, human curiosity and ingenuity still thrive. Reaching out into the unknown, guided by the faint whispers of data traveling billions of kilometers back to Earth, journey marks both a triumph of engineering and a poignant reminder of the finite nature of even our most enduring creations. Now, well over 46 years since its launch, Voyager 1 continues to drift deeper into the uncharted sea of interstellar space, carrying with it the legacy of Earth's first true attempt to reach beyond the confines of the Sun's domain. Yet, as the spacecraft travels ever farther, it faces increasing challenges. Its power supply, generated by radioisotope thermoelectric generators, RTGs, is gradually weakening. As of now, NASA engineers have been shutting down non-essential systems to conserve energy and extend the mission's lifespan. Sometime in the late 2020s or early 2030s, Voyager 1 will likely go silent, as its power becomes insufficient to sustain even the low-energy communications that still reach Earth today. Despite this inevitable silence, the spacecraft will not stop traveling. Long after it can no longer send signals or power its instruments, Voyager 1 will continue coasting through the Milky Way galaxy, a silent sentinel bearing the golden record, waiting for a distant intelligence, if such an intelligence exists, to encounter it. This golden record, painstakingly curated by a team led by Carl Sagan, includes readings in 55 languages, music from a wide range of cultures and eras, from Bach and Beethoven to traditional songs from Japan, Senegal, and Peru. Images depicting life on Earth, human anatomy, architecture, DNA structures, and the planet's ecosystems. Sounds of Earth, including the laughter of a child, the roar of the ocean, thunder, and the chirping of birds. These records serve as a kind of cosmic message in a bottle, not with the hope of rescue, but as a declaration: we were here. We reached for the stars. We tried to understand the universe and ourselves. In this way, Voyager 1 and Voyager 2 have transcended their original scientific missions. They have become monuments of human creativity and persistence, testaments to a civilization that dared to send its voice into the dark with no guarantee of reply. They represent an act of faith in the future, a belief that knowledge, wonder, and the desire to explore are enduring parts of what it means to be human. As we gaze toward the heavens, tracking the faint signals from these emissaries, we are reminded that our reach has already extended beyond the solar system, and that even in the cold emptiness of space, our story continues. The Voyager mission teaches us that the journey itself, filled with discovery, wonder, and enduring hope, is as important as the destination. Voyager 1's incredible journey has reignited the world's fascination with this fearless spacecraft after more than 4 decades of exploration. Voyager 1 has traveled far beyond our solar system, venturing deep into interstellar space. It has crossed the heliopause, the boundary where the sun's influence fades, and now drifts through a vast, uncharted region of the galaxy. In August 2022, Voyager 1 sent a mysterious message back to Earth, one that captured the imagination of scientists and space fans everywhere. Amid streams of data and telemetry, researchers detected a strange anomaly, an object of unknown origin and makeup. Tentatively named the Cosmic Enigma, this object is unlike anything ever encountered in the history of space exploration. What makes the Cosmic Enigma so puzzling? It emits faint, irregular signals that don't match any known natural celestial phenomena. Even more intriguing, its path through space seems deliberate, as if it's following a specific course through the cosmos. This discovery raises deep and fascinating questions. Where did this object come from? Who or what created it? And what might its intentions be? Scientists and astronomers around the world have been meticulously analyzing the data sent by Voyager 1, determined to unlock the secrets of the mysterious cosmic enigma. Could this baffling object be a remnant of an advanced extraterrestrial civilization, or perhaps a probe launched from a distant corner of the galaxy? Alternatively, might it be an entirely new and unknown cosmic phenomenon? The discovery has ignited a wave of speculation and debate, bringing together experts from diverse fields who are collaborating to unravel the enigma's true nature. One leading theory suggests that the cosmic enigma could be an ancient relic from a long-lost civilization, a probe dispatched eons ago, its original mission veiled in the mists of time. Whether its purpose was scientific, exploratory, or something beyond our imagination remains an intriguing mystery. On the other hand, some scientists propose that this object might be a natural celestial phenomenon, with properties that challenge our current understanding of astrophysics. This possibility reminds us of the universe's immense complexity and the vast diversity of cosmic phenomena still waiting to be discovered. It highlights how much we have yet to learn and how little of the universe's secrets we have uncovered. The detection of the cosmic enigma underscores the critical importance of continued space exploration. It calls for humanity to push further into the cosmos, to embrace the unknown, and to expand our cosmic reach. The universe is a vast, mysterious frontier, filled with wonders and enigmas that inspire awe and curiosity. As Voyager 1 continues its solitary voyage through interstellar space, carrying with it the mystery of the cosmic enigma, humanity stands on the brink of new discovery. This spacecraft has become Earth's ambassador to the stars, a shining symbol of our insatiable curiosity and unyielding desire to explore. Voyager 1's odyssey, spanning over 4 decades, has fundamentally reshaped our understanding of the universe. It continues to inspire generations of scientists, dreamers, and stargazers alike. As we ponder the mysteries of the cosmic enigma and the endless possibilities it represents, we are reminded that the cosmos is a vast, wondrous, and ever-evolving realm. Each new discovery brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? With its indomitable spirit and enduring mission, Voyager 1 carries our hopes and dreams as it forges onward into the cosmic unknown. The story of Voyager 1 is a testament to the enduring human spirit of exploration, curiosity, and the relentless quest for knowledge. It transcends time and space, reminding us of our place in the universe and the boundless wonders awaiting us in the cosmic expanse. The enigma of the cosmic enigma serves as a poignant reminder that the universe is filled with mysteries yet to be unraveled. It invites us to continue our cosmic journey with wonder and humility, ever eager to explore the depths of the unknown. Voyager 1, humanity's cosmic emissary, continues to inspire us to reach for the stars and embrace the infinite possibilities that lie beyond.